Hello, everyone. My name is Alex. I committed a crime. I invited everyone to this tutorial because I clicked the green button. I'm really sorry for everyone who was in another tutorial. In the upper left, there's a schedule button. And you can navigate back to the proper tutorial you were in. I am really sorry. The Crowdcast is defaulting to making me make mistakes. I mean, I take the blame, but
having said that, this tutorial will be very exciting. So if you feel like sticking around, it's deep learning from scratch with PyTorch, with Dhavide, Aruliah, and Hugo Bowne-Anderson. And Alex is a fantastic host. So we have people from Nairobi, from Austin, Texas, from the capital of COVID, Los Angeles. I'm glad to see there's still a sense of humor in some realms. You've been called a bad man, Alex, by Andrew.
I'm sorry. All right. I will go off screen now and I'll leave Dhavide and Hugo take the lead from here. So have fun, guys.
Thanks, Alex. And hi, Dhavide.
Hello, Hugo. It's nice to see you, sort of.
It's very nice to see and to converse. And hello, everybody. The reason I am not sharing my my visage currently is that I'm incapacitated. I've been having very extreme back spasms for several days, and I can't stand or sit. So will be teaching. This is the first time I've taught lying down. Although I have learnt in a hammock at one point. So we'll see how the tables have turned. Before we get going, it's also midnight for me in Sydney, Australia, for what that's worth. And Dhavide, is it 8 a.m.?
7 a.m.
7 a.m. So we're at opposite ends of the graveyard shift. And so you're in Vancouver, right?
That's right, yeah.
Yeah. Great. So I just wanted to thank you all for joining today. This is the first online SciPy, and we're very excited to be teaching here. I also wanted to thank SciPy for pulling this all together at this point in time. It's a huge amount of work, huge infrastructure.
I am gobsmacked at.
It's amazing, isn't it?
Yeah, it's.
And of course, Alex, who was just a host. There are lots of people working behind the scenes. I want to give a shout out to Jill Cowan, who I've been coming to SciPy for at least 5 years now. I consider SciPy a home away from home. And she has been, she's one of the unsung heroes of the entire PyData community in my eyes, with the work she's done to bring this conference together over the years as well.
Agreed. Yeah.
A couple of housekeeping things. In the GitHub repository, which I presume you all have access to. If you don't, just let us know wherever that.
Yeah, it's just posted in the chat. Let me do that again. Just.
Oh, this is so good. Everyone's saying Jill rocks. That's great. It's very true. So, and is that the chat in Slack, Dhavide, or?
Sorry, no, I'm using the Slack, the chat here on Crowdcast. I should actually have my Slack chat open as well, but unfortunately, I have that on a different machine.
Guys, I highly recommend sticking to the chat in here and maybe using Slack as to continue the conversation after the tutorial.
Got it.
But as much as possible, keep it in the inside of Crowdcast.
Yeah, no, that makes. Thank you, Alex. That's a good idea. But I think Alex's point is also an excellent one. So after the tutorial, we'll see how far we get. And if there are more questions that arise, then Hugo and I will be available to take on questions. So so those things can more deeper questions and inquiries and looking for links and sharing stuff with each other can happen in there as well throughout the rest of the conference and however long the Slack is open. So that's a good idea.
Yeah. Fantastic. And so also in the README at the top, I've got a feedback form. I'd really love, Dhavide and I would both really love for you to fill out this short feedback afterwards. That will help us improve this work. And of course, Jill just mentioned, I'd love to give a shout out to Kristen, who does a lot of work behind the scenes here as well. feedback is welcome. It was a few hours ago, there was a pull request for a typo in the README, and that was fantastic. So any questions, put them on the issue tracker. Issues are welcome. Pull requests are even more welcome. Particularly as this is a workshop, a tutorial on open source materials. So let's, in the open source spirit, let's get involved as much as possible. We'd really, really appreciate that. Great. So I think, without further ado, do we have a sense? Do most people have the environment up and running on Binder or Colab or anything like that?
Let's turn the question around. Does anybody not have the materials running? And mention it in the chat, and I'll try and see if I can help you offline. But otherwise, Hugo, I think you should start sharing your screen.
Fantastic.
And going forward.
Great. Fantastic. I'm just doing this. This is the first time I'm using Chrome because Google, and so now I need to. Oh, you're bloody kidding me! Google Chrome will not be able to share the contents of your screen, and Chrome is quit. So I will disappear for an instant, and I sincerely apologize for that.
So, wait. Are you still there?
Yep, I'm still here.
So were you sharing the application, the entire screen, or just a tab of Chrome? Strange things can happen depending on which you choose.
Yes, I was trying to share the entire screen. So I'm going to share. I
would say share the application. That's what I tend to do. And I think that'll be better.
Absolutely. Great. Look at that.
I'm on Windows for a change. Like I never. There we go. We see it, Hugo.
I'm on my cell phone. No, I'm kidding. That's not true at all. So click to close message. Fantastic. Now we see the infinite screen. Wow, that is really.
That's like
we're entering the vanishing point, aren't we? Okay, great. So what I'm going to do? Do you now see GitHub?
Yeah, we see GitHub.
Okay, so I'm going to launch Binder. So I'm going to open this link in a new tab. And Binder is an incredible resource that's developed and put together by great people in the PyData community who come from Project Jupyter as well. And it allows us to get learning materials up and running and you up and running without doing a whole bunch of crazy installs immediately. So I just want to give a shout out to them. I've been using Binder for years for these types of tutorials, and it's been such a blessing. You'll see here that I have Binder opening a Jupyter Lab interface where, I've got my launcher here where I can launch new notebooks, console, terminal, text file, that type of stuff. I also have my local file directory here. So we're going to jump into the notebooks. And what I'm going to get everyone to do is to open the first notebook, notebook 1, but the student version. And what that means is we're gonna write code together. There are going to be some hands-on exercises. If you need to dive into the instructor notebook at any point, before doing that, I just ask a question. Whatever's tripping you up, ask in the chat. Pardon me. Okay, so we're gonna jump in. We'll just wait for that to load. So this notebook, I'm already getting a bit croaky, unfortunately. This notebook will occupy us for the first half of this tutorial. And essentially we'll be kind of building up deep learning from scratch using NumPy, right? So just to talk you through what the learning objectives are, before we dive into the technical stuff, I just want to make clear that, and this is something we're seeing more and more, that machine learning is a technical field, but it's also a cultural, economic, and social discipline that has the ability to consolidate and rearrange power structures, among other things.
Hugo, quick question.
Absolutely.
Just to clarify, the student notebook versus the instructor notebook, the student has exercises that aren't filled out. The instructor ones are filled in. So if you get stuck because we're going too fast or something, it's always there for us. That's the
exactly. Yep.
Sorry, I wanted to make sure we said that because it came up.
No, please, and please anything that I miss at any point, please do mention. And the instructor notebook probably may have, let's say, more sophisticated code than what I will come up with on the fly as well, or let's say simpler code as well. So after we talk a bit about machine learning in general, and before we get into deep learning, I can hear a keyboard typing.
That's me. Sorry, dude. Yeah, let me mute.
Right. So before we jump into building deep learning models, essentially, I want to give a brief introduction to how to build simple machine learning models for classification and regression using Scikit-Learn. And then we'll get into using NumPy to hand code forward propagation for certain types of basic neural networks using NumPy. Then we'll start thinking about nonlinearities. Then we'll start thinking about optimizing our networks using gradient descent. And then we'll kind of discuss briefly the basics of back propagation, which is really how neural networks think about optimization. Okay, great. So as an intro to machine learning, there are a few things I want to say. So data science itself is often sliced into descriptive analytics, predictive analytics, and prescriptive analytics, which are essentially BI, classic analytics and dashboards. Then machine learning is predictive analytics, and prescriptive analytics is decision science, and how we incorporate data into the decision-making process. Machine learning itself is sliced into supervised learning, which we'll be working a lot with today. So this is predicting a label, such as classifying something or predicting a continuous variable. There's also unsupervised learning, which is pattern recognition for unlabeled data. A paradigm of this is clustering. And then there's reinforcement learning, in which software agents, as I've written here, are placed in environments and given rewards and punishments based on their activity and based on a lot of theory and behavioral psychology as well. And paradigms of this are AlphaGo Zero and self-driving cars. So this workshop, as we know, is an introduction to deep learning, which is a very powerful and impactful form of machine learning that just has been given a lot of attention for its successes, particularly in computer vision and natural language processing.
Hugo, can you make your fonts a little bigger? Maybe minimize the notebook, the browser on the left?
Absolutely. I'll also... How does that look?
Yeah, that's great. Better. And if you maybe you can just, if you hit the folder icon on the left, it'll fold up that tab.
Fantastic. Okay, so I just want to make clear at the outset that what we're doing aren't just building technical stuff, because I think it's easy to get kind of rolled up in the technicalities and have fun solving a lot of technical challenges. And so Cathy O'Neil, who's the author of a well-known book, Weapons of Math Destruction, has said, data science doesn't just predict the future, it creates the future, and it causes things in the world. So these are examples of a lot of harmful algorithms out there that I think we're probably all pretty aware of these days, but there are runaway feedback loops in predictive policing. And this happens in whereby more police are sent to neighborhoods with higher reported and predicted crime, resulting in more police being sent there and more reports of crime and so on. Google search is another example, which we talk about the challenges of Facebook a lot these days. We don't talk enough about the challenges of Google. So Google search encodes all types of cultural and societal biases. I recommend Sophia Noble's book, Algorithms of Oppression. And one example is that for many years, if you searched images for the word beautiful, the results would be dominated by photos of white women. And Ruha Benjamin, whose work I very much encourage you to check out, her book, Race After Technology, is fascinating and startling. She stated explicitly that race and technology are co-produced. On top of this, Cathy O'Neil, in her book, Weapons of Math Destruction, delves into the interaction effects between lots of these models that are deployed in society that mean they feed back into each other. So those demographics that are likely to be treated unfairly by healthcare algorithms are also more likely to be discriminated against models used in employment hiring flows and so on. And as I'm sure most of us are aware these days, the type of groups that are impacted most adversely are those who are already systematically oppressed, such as people of color, which of course is a very important conversation we're having currently. I also wanted to point out a few resources that these are a bunch of fantastic books dealing with this type of stuff, automating inequality, Ruha's Race After Technology, Algorithms of Oppression and Weapons of Math Destruction. I also just wanted to make a statement about the, I think, purported objectivity of data. And there's a wonderful recent book called Data Feminism, which delves into this. And in particular, the fact that data collection and data reporting are always either political acts or informed by politics and political processes that are embedded in societies that already have asymmetric power relations. Okay. And I'd also encourage you to check out Chris Wiggins, who's at Columbia, and he's the chief data scientist of the New York Times, and Matt Jones at Columbia have a course called Data Past, Present, and Future, where they data and statistics have consolidated and rearranged power structures over the past couple of centuries. And something I realized from their materials is that the etymology of the word statistics doesn't come from numbers at all. It comes from the term statecraft, okay, and the ability of states and governments to wield power through the control of data collection and reporting. I also just wanted to mention that when we're building algorithms, I think we really need to interrogate not only the algorithms we're building. So if you're thinking about building, facial recognition algorithms, I think it's pretty clear that we need to think long and hard about what purpose they actually serve these days, but also about the data that we're actually using. So as I've written here, be careful with the algorithms you build, how they're deployed, and also the features you use. So, for example, if you think race should not be a feature of your data, and I've written which it more than likely should not. I can't think of a single model where it should be off the top of my head. Then you should throw out zip code as well, also, because it's highly correlated with race and very often encodes it.
May I interject for a moment here, Hugo?
Please.
Yeah. So actually, Hugo and I had an interesting discussion while we were developing this tutorial. So one of the things that I wanted to try and do. I had a sort of a data set from some materials that I'd used before for training, for teaching, and Hugo and I had a discussion about whether or not to use it. And it was about it was gender classification based on voice samples, and it works quite well through this network. But it was a kind of the question that Hugo and I asked ourselves is like, why do we actually need to actually classify someone's gender on the basis of their voice? And it was a good question to ask, and we decided against using it because we sort of thought like this is kind of this isn't necessarily all that interesting. And I think if you look at a lot of machine learning materials out there, there's things like the Boston housing data set, which is one that has always bothered me, that actually has a strange feature in it associated with the number of African Americans living in this percentage living in a given region or something like that, which is then used as a predictor variable in housing prices, and there are other kinds of interesting challenges that are sort of put there throughout in a lot of the historical statistical learning, machine learning literature that sort of led into this discussion that Hugo has initiated here. So anyway, sorry, Hugo, I'll let you go back to it. But
no, that was great, and thank you for that extra context. I think that's very helpful for everyone here today. And I will add that it's deeply ingrained in so many parts of our culture. The Boston housing data set that you mentioned is actually one of the data sets that ships with Scikit-Learn, right? So that's something we really need to be thinking about. And I want to step back and correct myself slightly. I said I can't really think of a model where you would want to include race as a feature. There may be cases in which you want to interrogate whether particular races are systematically oppressed. And in that case, maybe you do want to include race as a feature to think about these types of questions. But these are the types of conversations I really think we need to be having. The second point I wanted to make, because it really informs one of the examples we get to in a second, is if you're given a data set with gender or biological sex as a feature, we should all be questioning why it was even collected in the first place and whether including it could discriminate against any gender or sex. And to my knowledge, it's always discriminatory against non-males. I'd be very interested to see any other cases that people would like to bring up.
As someone's just pointed out, that'll be the topic of Bonnie McLean's diversity talk later this afternoon about collecting data. I think it's specifically about race, but I think that it's an interesting question. Yeah,
absolutely. So as we'll see, we're now going to jump into a data set where sex is a feature and build our first machine learning model. So it's what is now the famous Titanic data set where each row is a passenger and the target variable, the one we're trying to predict, and we'll explain that more in a second, is whether they survived or not. The features, which are the variables we use to make the prediction, include name, the fare they paid, where they embarked, and their sex. So I just wanted to interrogate this for a second. Do we want to use this feature? So my rationale is I think we're okay doing it for the purposes of this. We're interested in building the best predictive model and not putting it into production. So we're not making decisions based around this and taking actions that impact lives. So it may be okay, but I encourage you to think about this question further. It's also credible that we could build a more accurate model by keeping sex as a feature. As it's documented on the Titanic, the captain explicitly issued an order for women and children to be saved first. Okay? So without further ado, I'd like to jump into some machine learning. My binder said, this is great. I've done this way too many times before, talk so long that my binder session times out after 10 minutes. And that may have happened to all of you, unfortunately. So when we got to run our first bit of code, we're going to have to restart this. Okay, so the target variable is the one we're trying to predict. Other variables are known as features. You may also see them called predictor variables. They're the ones you're using to predict the target. And I've got an extra parenthesis there, but I'm not going to, somebody can issue a pull request on that one. Maybe I'll do it myself. So that's on terminology. On process, practice, procedure. To build machine learning models, we really require two things: training data, which the algorithms learn from, and then an evaluation metric to gauge the performance of our algorithms. Now, there's one more point I want to make. If our ingredients are training data and evaluation metric, I just want to make a mention of all the types of biases and other problems you can then get in your algorithms and your models. So if your training data is biased, your model more than likely will be as well. And many of the examples I've cited already result from biased training data. On top of this, if you're optimizing solely for accuracy, what happens to groups that are underrepresented in your training data? So I'm going to leave that as a question. But we get less accurate results is one answer. There are a lot of other things that can go wrong. But the latter challenge really follows from a class of problems we face when optimizing anything. And I would very much encourage you to check out Rachel Thomas's post. Wonderful blog post. The problem with metrics is a big problem for AI. And it's really the problem with the fact that all metrics that we optimize for are actually essentially proxies for what we really want to think about, okay? And that they are gamed a lot of the time. So I'll encourage you to check out Rachel's post there. So without further ado, let's restart this kernel. I just wonder if I can restart the kernel or, yep, great. So everybody, let's execute this first cell. And I did that holding shift and pressing return, okay? And we're doing a whole bunch of imports here. We're importing NumPy, Pandas, Matplotlib, Seaborn for data viz, a few things from Scikit-Learn for machine learning. Then I'm using some magic, IPython magic to get all our figures in the notebook as opposed to saving them elsewhere. And I'm using sns.set, that's Seaborn. You see I've aliased Seaborn as SNS to just make the visualizations slightly more pleasing to my eye anyway. Okay, so now we're going to import the data. So we're going to use Pandas to read this CSV file, which is in the GitHub repository, into the data frame df. And we're going to view the first lines of the data by looking at the head. So that's just applying the method head to df. And I think the default argument is 5, but we can just, okay, great. So now we're looking at our training data. Okay, we can see we have the ID of the passenger, whether they survived or not. So this is what we're trying to predict, what class they're in, the name, sex, age, and so on. Okay. So I encourage you to play around a bit more with that in your own time. If you haven't seen this data set before, I suppose one thing I'm doing here is basic exploratory data and analysis before even visualizing anything, just to get a sense of what our data looks like, which we definitely should do before building any models at all. To check out the data types, I'm going to use the info method, and we'll see there that, okay, what this tells us is that we have 891 rows. We have, these are all the columns, some of which I mentioned before. We'll see passenger ID is an int, survived is an int, class is an int, then name and sex are objects, which are the most general types, which are in essentially strings most of the time. Then we have some floats. Another thing I'll point out is that, it tells us about memory usage, for example. It doesn't matter so much at the moment, but we'll see that most of our features have 891 non-null entries, but some of them have a few less. So age has 714, cabin has 204, embarked has a few less, or two less, in fact. So what we see there is that there are missing entries, which is something we will have to think a bit about soon, okay? And also, just for context, we're nearly half an hour in. I'm planning to get through this initial machine learning section, hopefully in 20 to 30 minutes, and then we'll have a break if that works for everyone. And if in the chat people want a break earlier, Dhavide can let me know. So to check out the summary statistics, it's nice just to get a sense of, what the average age and the median age of people were. Just do a bit of exploratory analysis. We use the describe method there. So yeah, let's look at age. We can see the mean age was nearly 30. The median age was around the same, was 28, okay? Then this is the fair paid. We haven't discussed that feature yet. We can see the mean was 32. Whatever units these are, it doesn't really matter at the moment. Whereas the median, which is the 50th percentile, was 14. So what that suggests for those slightly statistically savvy is that we probably had a bunch of outliers up the top, and that makes sense. If you're going in first class, that's a pretty serious jump up there, okay? To drag the mean up, okay? So unless there are any questions, well, yeah, are there any questions with that, Dhavide? Has anything popped up so far?
No, I'm just troubleshooting a particular technical problem someone having, but I'll let you keep going.
For sure. Okay. So now we're going to do a bit more exploratory data analysis and build some first models. So I've written here a huge part of model building is making sure that our models generalize to new data. Okay. So essentially, one way to think of that is that we want our models to capture the signal in the data and not the noise or fluctuations in the training data, right? So if it's capturing, I can hear your keyboard again, Dhavide, if you wouldn't mind muting.
Oh, sorry.
That's okay. So if it's capturing a lot of the noise, we call this overfitting. And this is an image that I got from Stack Exchange, actually. I think, is that? Yeah, that's right. Which is a nice schematic. Okay, so we can see this is, if you just look at the data here, it's some sort of non-linear curve. Maybe a quadratic could deal with that. I think it probably could. So if we fit a line, then we're underfitting because we're not capturing all of the signal. If we fit something like this, it looks pretty good. Now, if we're fitting this, which actually goes through a lot of the data, even more of the data than this one does, it's overfitting because we're capturing a lot of the noise and it's not going to generalize that well to new data, okay? The reason I'm mentioning this now is because when we're building models, right, particularly predictive models, we don't want to look at all the data at the start. We want to hold out some of the data into a test set, also called a holdout set, so that when we train the model on the training data on the subset, we can then see how well it performs on the set we've held out, okay? So to that end, key terminology, Training data is what we train our machine learning models on. Test data or a holdout set is what we use to gauge how well our model performs after we train it. Okay. There's a slightly more sophisticated alternative called cross-validation. We'll cover it here. Feel free to check it out. This is probably Scikit-Learn documentation. Yeah, I'm just going to, let's see. I'm just going to open this, and I just want to give a shout out to the Scikit-Learn documentation, actually. It is so wonderful. And cross-validation, for example, is wonderfully explained. But definitely a lot of great machine learning resources there. So let's have some fun. We're going to split our data into train and test sets. And Scikit-Learn has a pretty cool utility function to do that, which is called train test split. So your notebook should look like mine at the moment. We're going to import train test split from scikit-learn.model selection. So what I'm going to do is I'm going to start typing it, then hit tab, and hopefully get some sort of autocomplete vibe. Okay, that's good. It auto-completed it for me. Okay, so now we have this function. I'm going to, essentially what this does here is I'm going to take the original data and create a training set and a test set. But I'm going to split both of those into predictor variables. So that will be these, and then the target variables. So this will be the survived column that we're trying to predict. And train test split unpacks it into a tuple for us. So that's all good, and we'll see that. So I'm going to call train test split here. And what I'm going to do, there's actually a bunch more code, but there are a few arguments to it which are actually important, very important. So the first thing I want to pass it is the predictor variables or the features. I don't want to pass it the target. Okay, so that's the data frame, but I want to drop the survived column. Okay, so I'm going to do data frame, and I'm going to drop the survived column. Now, a quirk, or let's say a feature of Pandas, is that it will first try to drop a row, not a column. So I need to explicitly specify that I'm dropping a column. Okay, so after I specify the predictor variables, now I'm going to specify the target. Okay, which is df survived. And this, of course, this is a bit convoluted for the first bunch of code to write. I just want to make clear that we won't be doing a lot of scikit-learn code, but I think it's important to see how train test split actually works. Okay. Then I want to give a test size, so tell how much to save for testing and for training. So I'm going to use a third for that. Now I'm going to set a random state. What this does, it ensures reproducibility. Okay, so what this train test split, it uses a random number generator to do the split, and what this will do is it means if I run it again, it'll give me the same split. Now, the last thing I'm going to do is I'm going to stratify this split. Now, what a stratified split essentially is, it means that when I split it, I don't want all of our, survived going into the training and all of our not survived going into the testing. So what it will do, it will preserve the target variable Sorry,
Hugo, you've just been asked, can you explain that drop in pandas again? Someone didn't quite...
Oh, yeah. Okay. So the rationale behind dropping is that the first argument to train test split will be the predictor variables. So we don't want the survived column of our data frame, right? Which we don't want this column, right? Now, so I'll drop the survived column, but I need to tell Pandas that I want it to be a column, not a row. Okay. Axis is equal to 0 would make it a row. Axis is equal to 1 makes it a column. Okay. So that's the rationale there. So great. I've executed that. Now I want to make a bar plot of the target variable of survived. So now I'm going to do something slightly quirky where I'm actually, remember in the training data set, df train is the predictor variables and ytrain is the target variable. So I'm going to create a new column of survived called ytrain. Okay. y_train. Then I'm going to use Seaborn to make a bar plot. And I think it's called count plot. Let's just, good. So for count plot, the first argument is actually...
Sorry, Hugo. So there was a question about explaining stratification again, and can you stratify on all features?
Oh, that's a good question. I'll leave that as an exercise for the reader to check out the Scikit-Learn documentation. I'm not certain. It may be the case, and it'll be a function. I mean, technically you can. I don't know if Scikit-Learn allows you to, but often you really only want to stratify according to the target variable. Okay, so what I'm going to, and so the second keyword argument here is the data set itself. So we're building a count plot, a bar plot. Okay, great. So what we see, and it's good that we stratified, right? Because what we see is that, nearly 250 people survived and over 300 did not, okay, in the training data set. I know from the documentation as well that survived 1 means survived and 0 does not, but I'd encourage you to check that out. It also gives some output with respect to the figure. I can remove that by giving a semicolon there, so that just suppresses output. I think it's important, though. I see a lot of people say, wow, Seaborn's great. Why doesn't Matplotlib have all of this stuff? Seaborn is built on top of Matplotlib is the short answer to that. And Matplotlib is a base that a lot of different packages, including, basic pandas plotting methods of data frames uses. So I just wanted to give a huge shout out to everyone who has ever and continues to and will in the future work on Matplotlib to make packages like Seaborn possible, which is also a fantastic package. So I'm going to execute again with that semicolon just to remove that. Okay. So more people died than survived on the Titanic. So let's just make a really naive baseline prediction that everybody died. We know they didn't. So this is a bad model, but it will give us a baseline against which to compare any future model we build. So what I mean by that is if we predict this and see on the test set that we get a certain accuracy, then we know that any model we build will need to beat this in terms of accuracy. Okay. So what I'm doing here is I'm setting a survived column of test equal to 0. And now what I'm going to do is compute the difference between this and actual survival. So the difference between the prediction and what we actually get, let me get this right, is so y test minus EF test, and this is survived. Now, I'm not sure if I need this, but I get into trouble with this all the time. This will return a pandas series, an actual data frame. And so I'm going to turn it into an array. So we know that this is just going to be a series of zeros. So actually, we could just do that. But if it was something else, this is generalizable code. So this will tell us the difference row-wise in the test set. So to get the actual accuracy, I'm going to sum up the difference, divide by the length, and this will tell us the fraction of incorrect results. So 1 minus that will give us the accuracy. Okay. So that's the proportion of actually correct results. So let's print the accuracy. Okay. So what we see there is that it's 61.7% accurate. So that means if we just made a naive prediction that everyone passed away, nobody survived on the Titanic, this would be a model which is 61.7% accurate. Okay. So what this tells us is that any model we build definitely needs to perform better than this. Okay. So now we're going to build a model called a decision tree. Okay. it kind of it's analogous to what you would think of as a decision tree in general. But we'll get to that. We actually need a bit of data preparation. As we saw, there were missing values. So what I'm doing here is imputing missing values. So we're filling all missing values of ages with the median, and similarly with the fair. So after we do that, just want to check out the info, and we'll see, yep, we've got all values for everything except cabin and embarked, and we're not going to use those two. Okay. What we're also going to do is convert sex into a numerical feature, and I won't say much more about that at the moment. And then we're going to select these columns. Okay. So what I'm going to do is view the head of what happens when we do this, and we'll see that the sex feature, which was male and female, has now been changed to a sex male column, and 1 for male and 0 for female. Okay. We're going to do our train test split again into df train, df test, etc. Now, I should make clear the reason I did this all again. I did the train test split. All of this pre-processing and slight feature engineering, we wanted to do on the entire data set before doing the train test split, so that all rows are treated equally, essentially. Okay. So now it's time to train your model. So we're going to build a decision tree. And what the training process actually does, it figures out the optimal ways to split the tree. Okay. So this is actually a bit big at the moment. Okay. That didn't do much. Essentially, this schematic will say if, here we go. If the sex was male, so that's sex male less than 0.5, so is equal to 0. Then we go down here, and that's the class survived. If the passenger was male, goes down here, and they died. Okay, so that's kind of the brief schematic of what a decision tree looks like, and I'm not going to go into the actual optimization process, but as I said, essentially, training the model chooses how these splits actually happen. Okay, but what I want to give a sense of is the Scikit-Learn API here. Okay, so what I'm going to do is I'm going to build a model. So to first do that, I want to instantiate or create the model object. To do that, I'm creating a tree. So I do tree.decision tree, and it's classification, right? Now, I want to make sure my tree doesn't go too deep, because if you go deeper and deeper and deeper, you'll end up overfitting. And we'll see how that works in a second. So I'm going to use max depth and make the max depth so equal to 3. So that would be 3 steps down. Okay. So fitting to data, the way we do it is we instantiate that model, then we do CLF dot fit. I pass it 2 arguments. The first are the features. So that would be df train of what I want to train it on. And the second argument is the target variable, which is going to be y train. Okay. Well, now I'm executing that cell with shift enter. That outputs kind of what we've created there. Okay. So now I want to make predictions on the test data. I've written here, store it in survived column, and that actually, I'm not doing that for the time being. So I'm just going to delete that, but we're going to make the predictions. And so we've used fit here. We use clf.predict now. And I know that Andy Muller, who's a core contributor and co-maintainer of Scikit-Learn, when he teaches his first 4-hour workshop on Scikit-Learn, the one thing he wants to make sure everyone comes away with is the ability to work with fit and predict. So essentially, this is kind of the basis of machine learning with Scikit-Learn and a lot of other packages, of course. But the Scikit-Learn API is one of wonderful beauty and elegance. So now we want to predict on the test set. So I pass it 1 argument, df_test. And what I'm going to do is just have a look at this output to see what the predictions are. Okay. It's what we'd expect in the sense that we get an array of zeros and ones, okay, of survived and not survived. So what I want to do now is compute the accuracy of this model. And we did it by hand before, but there's a pretty cool utility function in Scikit-Learn method. On CLF, I can apply the method score and then pass it the test set, and then what I know the actual labels are, which is wide.test. And what it does is it then makes predictions on this, like we did by hand there, and then compares them to the actual labels and tells us the accuracy of the model, okay? Cool. So we've built a decision tree of depth 3, which, you know, has increased the lift compared to our very naive model, gives us an accuracy of 86.8, which is pretty cool. I just want to actually confirm. I'm going to insert. Yes. Sorry,
Hugo. Just a request. I think you can slow it down a little bit. It's the scrolling through things is actually it's a little bit too fast for us to follow at the same time. So you feel free to slow down.
Okay, I appreciate that. Thank you. So CLF.score, what I'm doing here, this is a pretty cool way to just an IPython, some IPython fun to check out what methods or what functions actually do. So put a question mark and then put score, and we'll see that this CLF.score, great doc string, it returns the mean accuracy on the given test data and labels. Okay, so that's just to confirm that it is actually computing the accuracy. If you haven't seen the question mark before, that's pretty cool. Okay. Well, this is very exciting now because let's take 10 minutes for you all to do a hands-on. So this is fitting and predicting with decision trees and plotting the machine learning curves, the ML learning curves. Essentially what that does is, what I'm going to get you to do, I've got the template code here, is to, let me get this right, plot the accuracy as you increase the depth of a decision tree, plot the accuracy of the model on the training data and then on the test data. And what you'll hopefully see, and what we'll see, is that as you get deeper and deeper, you get better and better predictions on the training data, but you then at some point get worse and worse predictions on the test data. And this is overfitting. So what I'll get you all to do is just take 10 minutes now to go through this code. I'll maybe talk you through what's happening, the boilerplate here. So I've set up arrays to store the accuracies, and then we're looping over different values of the max depth. So I'll get you to set up a decision tree classifier like I did above. Then I'll get you to fit it to the training data. Then I'll get you to compute it on the training data. And then I'll get you to compute it on the testing data and then execute that. And so just to be clear, this line of code here, okay, you've got to complete 4 lines of code. 3 of them are almost exactly the same as code that I wrote previously. So setting up the decision tree classifier is the same. Fitting the classifier is the same. Computing the accuracy on the test set is the same. What I haven't done is compute it on the training set, but hopefully you'll be able to use this one to do so. So let's take 5 to 10 minutes to walk through that. So I'll give you that time, and then we'll come back and I'll write the code. And in the meantime, I'm just going to take a bio break myself, unless I
got it, Hugo. You take care.
Fantastic, thank you.
So yeah, sorry guys. I will. I'm here and I'm trying to follow in the chat as well, and also follow the answers and questions. But so Jenna, I'll try and take some of these while Hugo is off. And I could, yeah, I mean, you're right. I apologize. We were probably going a little bit fast there. And I was trying to follow in the chat and the question and answer box to try and keep up. So, but I thank you very much for slowing us down, because I think it's a little bit weird trying to teach in this particular way. So yeah, Jenna, I don't understand what a decision is and what it's doing. So a decision tree is a particular kind of machine learning algorithm. That can be used for classification or regression problems. And what it's doing is fundamentally splitting on individual. Let's see, actually, can I take care of the screen sharing? Yeah, I don't have, why don't I do it? Yeah, I'll try it right now while Hugo's away. And let me do my application window. And I'm now sharing. Let me just quickly just see if I can go. There we go. I just want something that has some pictures in it. So a decision tree is kind of a rule-based way of classifying things. So, for instance, here you've got something here that I guess is based on, it's you have instances, objects that come into your classifier, and you basically use different features to determine what. This is a really strange, what categories it would end up in at the end, right? Or maybe like a flow chart, right? Like whether the offer is going to be 30K or whether it'll be here. This is a regression type of example, I guess, like whether it's going to be 2.5K and things of that nature. So it's a strategy that's baked into Scikit-Learn. And so there are ways that so Hugo's notebook there has examples using Scikit-Learn objects that you can instantiate that have fit predict methods. This sort of very standard interface. Oh, thank you, Tihana. Oh, wonderful. Okay, thank you, Jenna. Yeah, no, and by the way, I want to thank you, everyone here who's been very lively in the chat. I'm trying to keep track of all of these things and make sure I'm filling in at the same time. So, and it's a little bit unnerving actually having this many people when I can't actually see any of you. So, I hope that we are able to. Let me stop sharing. How do I stop sharing again? Oh yeah, down there. And Hugo, are you back? You are not back. All right, let me, you guys have some time to work on your exercises. Has anybody done the exercise already? Okay. Well, thank you for the love. Okay, so we've got a few yeses here. Okay, done. All right, Hugo, are you back? All right, let me see if I can. Oh shoot. Oh, my binder has died because I have not been doing this, of course. All right. Well, why don't you all? Sorry. Yeah. Why don't we take 5? Stand up and stretch. I've got 4 minutes to the hour, so why don't we actually try and reconvene in 4 minutes, and then we'll work. We'll pick up, and hopefully Hugo will be back by then as well. remember. That is k equals 3 the best depth? That is, or k equals 5? That is an extremely interesting question. So let me repeat the question. So what is the best depth? And this is a difficult question to answer generically with using decision trees or with using any particular classifier to solve in supervised machine learning. So the question is, when you have a data set and you want to build a classifier from, so it'll classify into some groups: red, green, blue, yes, no, whatever, positive, negative. The question that has been posed is, how do you know what the depth argument is to use in the decision tree? And sometimes if you just let it will go as deep as it possibly can. So max depth, as someone is just pointing out, thank you, Prabal, is what you would refer to as a hyperparameter in a machine learning, in a supervised learning technique. And what you can do is you can play around with those, tune it on your training set, and you can get different behaviors, and you get a different model at the end of it. And what you hope to do is, at the end of it, you try with a few parameters, and then see what comes out of it. So Hugo, it looks like you're back now.
Oh, yes, I am back. I just didn't have my microphone on. Hey, everyone. I thought I'd just start writing code as Dhavide was wonderfully explaining hyperparameters and hyperparameter tuning and all of these types of things, which I commonly refer to as part of the Zen of machine learning.
Seriously. I
mean, sometimes you'll just be like writing stuff down on a piece of paper as well. It's really, for something arguably very scientific, there's a certain real craft and art that goes into it. Did some people were some people able to generate a figure, a plot that made some sort of sense? I'm not looking at the chat, so
yeah, I know. Sorry, I'm looking. I'm not getting any. The videos are all toggled off. All good. Wait. Are we back on? I can see the videos. Okay, no, we're back now. Sorry. Just let me.
Sure.
Okay, we're getting yes. Okay, people. Yes, we're getting a bunch of yeses now. People have the figure.
Yes, right, we can see you, and we can see the Hugo screen. So
my question was, were people able to generate the actual plot from the cell?
And the answer is yes.
So hopefully I've written the correct code. It's now 1 a.m. so we'll see how this goes. But so here I've built a classifier with max depth equal to k, where k is going, and I partially apologize for using enumerate here because I didn't actually need it. I must have wanted to store the I somewhere else previously. But essentially we're looping over the max depths, then I'm fitting to the training data, then I'm computing the accuracy here and storing it in train accuracy on the training set. Then I'm doing the same for the test set. And this is boilerplate code to generate a plot, which I hope. Okay. Oh, thank goodness. I can hear you typing, Dhavide.
Yeah, sorry.
That's all right. No, I think it's a nice gag.
Yeah, hang on.
We should
just let me. I was trying to answer a question, but maybe you should answer the question.
Sure.
Someone. Someone has answered in the chat as well. But it was about. Aren't we supposed to use .predict and use .score instead? Can you just explain a little bit what .score does?
Yes, absolutely. So .score internally uses .predict in order to compute the prediction, and then compares the prediction from the first argument, which are the predictor variables, with the target variable and computes the accuracy there. So essentially, we're computing accuracy time and time again for different depths. And what I really wanted us all to see here is that as we get deeper and deeper, the accuracy, as we tune this, as we increase the depth, the hyperparameter, the accuracy increases essentially because we're able to make more and more decisions to fit to the training data. And so we're essentially overfitting to it because we see the accuracy is going down and down for the training data. So there was a great question. Is depth 5 the best here? With this limited training data set and a decision tree, I would go with depth 5 because it looks like with depth 5, we've got something which generalizes pretty well from training to test data set. Okay. So I'm not going to talk a lot about regression. What I will say is that here we were predicting a categorical variable. We're classifying survived or not. Regression predicts a continuous variable, okay, such as the price of something. So we're not going to go through this regression example here, but I encourage you to do so after the fact, because what I really want to get onto is neural networks. But I'd like to ask Alex and everyone out there, would this be a good time to just let everyone have maybe it's 3 past the hour, a 5 to 7 minute break, so we could come back and start at 10 past?
We kind of, so when you did the exercise, I think people got through that fairly quickly. So while you took a break, I think a lot of us took a break. Unless I'm speaking, if anyone does actually think like we're like cooling down our brains for a few minutes, this is a good place in terms of the split of the material. So can I just get a yes or a no in the chat? Just to see whether or not yes or no to a Blake +1 or -1, yes, no, some kind of consistent signal. 10 minutes, please. I'm seeing from 1. A couple of keep goings. Keep going. I took a break. No, oh dear. I think the consensus seems to be to keep going, with my apologies to the person who did need a break.
Why don't we take I think we should take 5 minutes. We are here, well, all the
4 hours. Yeah, it's a long time.
Take 5 minutes. I think that's probably for the best. And
okay.
Even people who didn't want to break, I think it'll be good for all of us to kind of regroup and those types of things. So we'll see you back here in 5.
Oh, poll is up. Here we are. Yeah, sorry, there is a poll here. Thank you. How did we do that? Okay.
So we can use the poll next time. I do suggest we take 5 now, I think.
Yeah, let's do it.
Great. So I'm going to stop sharing and back in 5.
All right. I'm going to stand up and take a break myself. I will be back momentarily. Yeah, okay. Give me 2 minutes.
Dhavide, I would err on the side of not going through regression because I actually think we'll get a sense of it as we go through, and I don't want to penalize people who are taking a break.
Yeah.
And so we'll go through
overload. Yeah.
Thanks, James, for the comments about the back. I really appreciate it. And Esteban's suggestion to play the guitar is fantastic as well. Ahmed had a question. Yeah, we would say the model overfits after depth is equal to 5. Absolutely. So I'm just going to take a little break as well, my friends, and I'll be back in a few minutes. All right, everybody, we're back. Can someone just type or say hello to confirm that you can hear me?
I got you, Hugo.
Fantastic, Dhavide. So it's now time to dive into neural networks, which is what we're here for. So neural networks essentially are machine learning models that are loosely inspired by biological neural networks. And they've proven to be quite good for image classification, natural language processing.
Sorry, Hugo. I just want to say one thing quickly. So someone was asking about just posing questions in the chat. If you actually pose questions using the ask a question box, or you're prompted to do that when you put something in the chat, that actually makes a timestamp, and then we can record it, and I'll try and answer them there as well. And Hugo will do those while I'm teaching. So if you want our expertise, that's actually a better way to do it. Put it into the ask a question when you're ready there. So no screen. Are you screen sharing, Hugo?
I am now.
He's sharing now.
And I suppose there are two remarks there. It is slightly a shame that we need to use Crowdcast for the questions, because if we were using Slack, we could get upvotes. People could just give a thumb up for them, and then if one person asks a question and 20 people give a thumb up, that really helps to know how much time we should dedicate to it.
That might be doable here as well. I'm just not sure how to do it.
Yeah. The other thing, unfortunately, Dhavide, by the time your half starts, it'll be 2 a.m. here, and it will be very unlikely that I'll be able to stick around, unfortunately. And I apologize for that, but
no, that's cool, man. Don't sweat it. We'll just deal with it.
So my screen is being shared now. And as I was saying, machine learning models, neural networks and ML models loosely inspired by biological neural networks. But I'd leave it at that. I think in the cultural consciousness, sometimes there's a sense that neural networks behave like human minds and human brains and that type of stuff. And I'd like to dissuade you all of that myth. So essentially, when we're looking at neural networks, and we'll get a sense of how they actually work in a minute, but we have an input layer where we put an image in or put our data in, then it travels through a bunch of hidden layers and then an output layer, and it will output, George Washington in this case, right? And it will learn, quote unquote, features. And I say quote unquote because, machine learning tends to anthropomorphize a lot of its techniques. And I want to dissuade everyone of that as well. And so finally, we get some sort of prediction at the end in the output layer. Okay? So there are two main parts of these types of networks. We use a procedure called forward propagation, and that's when we train networks. When making the predictions, we use forward propagation. So that is taking an image, for example, or whatever our input data is, and propagating it forward through the network, okay? Then, when training neural networks, that's figuring out what all the hyperparameters are inside, which we'll see are called weights. We do backward propagation because we take the output and then alter the weights as we move backwards through it, and we'll see what that actually looks like soon, okay? So forward propagation is for prediction, and backward propagation is for training, so analogous to .fit. So let's first jump into forward propagation, okay? So the first example I want to go through is called the single layer perceptron. And don't worry about that seemingly complex term because it is definitely less complex than most neural networks that we'll see. The parameters that change when we train the model are called weights, okay? And so what we have here, we have inputs coming in, and each predictor variable we multiply by a weight. So the first one we multiply by the first weight, second one by the second weight, third one by the third weight, etc. And we have a constant which is just 1, which we multiply by a weight. So this is often called the bias, as we'll see. So this is just some constant, which we don't multiply by an input. Then we sum them all together, okay? So this is a weighted sum, right? So we're multiplying them by weights, adding them together, and then this will give us a number. So if we're performing regression, the weighted sum could just be the regression. If we're performing classification, we want to turn it into, in the binary case, either zeros or ones or something along those lines, A's or B's, X's or Y's. And we use a step function, for example, for that. And we'll see an example of that in a minute, okay? So that's pretty much what I've said here. To build the weighted sum, we take each input feature, x underscore I, multiply it by the relevant weight, and add them all up. This is essentially a weighted average when we're not dividing by the number. Okay, so if all the weights are 1 over n, where n is the number of inputs, the weighted sum is the average of the features. So in a lot of ways, it is a weighted average. Okay, a few more rules of thumb. If a weight is 0, then so if wn here was 0, xn times 0 would be 0 and would not contribute to the weighted sum. If a weight wi is greater than a weight wj, then the corresponding xi contributes more to the weighted sum than wj. So that's why they're called weights. They're how much we're actually weighting, how much importance we're giving to these features. Okay. So we're going to code this up in NumPy, and in NumPy, x and w will be one-dimensional arrays. Okay. So to compute the weighted sum, you can take element-wise products of these arrays and then take the sum. Now, it's not necessary to know any linear algebra here, but if you do know a bit, you may recognize that we can think of x and y as vectors and that the weighted sum is the dot product of these vectors. But once again, you don't need to worry about that if you don't know it. But for ease of writing code, we're going to use NumPy dot function and pass it the relevant arrays. I'd encourage you, if you'd like, to confirm that the dot product does produce the weighted sum just by working through several examples. So we're going to use a toy data set. We're going to use a toy example of an e-commerce website in which the features are, for example, the amount of time on the website, number of interactions, number of customer support interactions, and the target amount is the amount spent in a year. And if it's negative, we can interpret it as refunds or something along those lines. And that's a regression challenge because we're predicting a continuous variable, okay, an amount. So this may not be this actually isn't a good use case for deep learning, whereas image classification is, but it has the benefit of providing a really nice example for tutorial purposes. Also, the research scientist in me says, wait, where are our units? And we don't care about units currently. You can normalize them, whatever, but we don't care about them. In a real world case, you definitely would. Okay? So we're going to do this for NumPy, for one data point in NumPy. So we're going to execute. I've got no kernel because I've spoken for so long and we took a break. So where is my kernel? I'm going to restart kernel. Now, instead, I could go up and re-execute my imports, but I'm just going to import NumPy as NP. And you could actually, look, you can just do that in this cell as well. And I'm going to define one input data point here. And then we're going to build a little neural network, a little single layer perception on that, okay? So we've got an array with entries 10, which is the amount of time on website, 29 number of interactions, 2 number of customer support interactions. So I want to set the weights. I've set the bias, which was the W0 above. Then I want to compute the weighted sum plus the bias. So for the weights, remember we want one weight for each feature, okay? So I could just create an array, and I'm actually going to do that, but I'm going to randomly generate it using numpy.random.normal. Okay, so this will just generate me 3 numbers from a normal distribution. And to tell it I want 3, I'm going to specify size is equal to 3. Now, to compute the weighted sum plus the bias, remember I said we can do np.dot. There are other ways to do this. I'm going to do x, y, plus the bias, which is 0 in this case. And I'm going to print the result, okay? And that is output 6.08, right? So these were random numbers. Later on, we'll see how we can actually, usually you'll initialize your weights as something and then do optimization to figure out what the best weights actually are. But what we've actually done here together, now I'm going to scroll up for a second. This is a single layer perceptron, and we've done this. We've computed the weighted sum of all of these and added a bias term. The bias is 0, but we've actually just built a single layer perceptron in the regression case. Now, single layer perceptrons usually classically are used for classification, but we've done it in the regression case. And what I want you to do now is do exactly the same for one data point, but make it for classification, not regression, okay? And what I want you to do, remember this output a float. What I want you to do is to do the same, but output.
Hugo, pardon me. I just wanted to interject just because. We didn't. I don't think you fixed the random seed before you did that. So other people, I think people are getting different numbers and they're just confused about that.
Oh, yeah.
I just wanted to point out. Yeah, when you do random number generation, if we haven't fixed the seed yet, then you'll be seeing different things. But maybe, why don't you put one up there, set it first, and then re-execute it, and then that way people can do that.
Exactly. So I'm going to set a seed, but as Dhavide was saying, so a random number generator in a computer is actually a pseudo-random number generator, which starts with a seed and then generates pseudo-random numbers using an algorithm from that, which essentially are as random as we can get using computation. Now, what I'm doing here in Python, in NumPy, is setting the seed to guarantee a reproducible results. So we should get the same result if we all do this now. So we should all get 2.252, etc.
Yep.
Great. That's really good. I've actually done that before and it hasn't worked because somebody has something else has gone wrong.
Because some archaic operating system or something.
Yeah, exactly. Fantastic. So that's great. So as I said, I'd love for you to take 5 minutes or so it's pretty much the same code as here. And then I want you to threshold the output of the regressor using a step function. And this may involve you Googling step function in NumPy or something like that. I actually don't know. But if you can't figure it out, ask in the chat. Pete, maybe others will help you out. But I'd encourage you to have a look before looking for the answer in the chat and asking for it. So let's take 5 minutes for this. And if there are any questions in the meantime, Dhavide and I will happily field them.
What is the threshold for the step function? So Tiago, sorry, I don't quite follow your question.
I think perhaps the answer is it doesn't matter. You can choose, because we're just building a very simple network where we haven't trained it at all. All I want you to do is give any step function. There are a couple of more obvious ones, I think. But I'll actually just bring up for those watching what a step function actually is. Well, okay. Maybe I'll go back. Yeah, so this is an example of a step function which is, I can hear you typing, Dhavide.
Sorry.
No, that's all right.
I keep forgetting.
It's great. So this is an example of a step function which above 0 you get 1 and less than 0 you get 0. So I honestly, the code you write now, I don't mind what step function you use. Just one to see that you output something binary. And at the risk of getting infinite screens, I'm just going to look in the... Ethan has a great question. In a real-world problem, would you have to compute the bias using a separate algorithm? Oh, yeah. Great. Dhavide has answered it. There we go. Maurizio, you can use a sigmoid, and then maybe you need to threshold it somehow. That's what I do below. There may even be a more obvious one initially, but I'm gonna start writing this code just to get into the swing of things. I'm gonna do np. Oh no, I want it normal. Size equal 3 again. Not compute the. Okay, so I think it's time for me to let you know what step function I would have used initially. I mean, the most straightforward one in my mind, and you may have another one, is np.sign. Okay, so what that does is it'll output 1 for positive and -1 for negative.
So one question also, Hugo, just to refer to when you're answering. Someone has asked, what exactly is the bias for? So maybe you can address that while you're going through this.
Yeah, that's a good question. The bias essentially is to account for shifts that we don't get in the input data, is how I'd describe it. Does that sync with how you think about it, Dhavide?
Actually, so the way I think of it is, thinking of the analogy with neurons firing, right? So usually if you think about neurons firing, which is there's some kind of a buildup, a chemical buildup. I'm not a biologist. I don't know, which basically once it reaches a certain amount of concentration of chemical in the neuron, it'll fire and then transmit an electrical signal down the axon. So I think the way to think of as a biological metaphor is, when does it actually trigger, right? Like how far? So the bias changes that threshold level at which something will actually happen, and then the neuron will propagate a signal down to the next neuron in the layer. And when we look at neural networks coming up and multi-layer perceptrons, that's actually a really important way of thinking of the biases. So,
yeah, and I think that holds in the classification aspect as well. I think in the regression aspect, it's really essentially just a shift to. It's essentially a linear shift to get everything aligned in kind of in the right space, if that makes sense, or even at the right order of magnitude. Are there any questions about what we've just done? Are you still there, Dhavide? I seem to have lost you. I'm not sure.
No, I'm here. My video's off to avoid taking screen real estate.
Yep.
And then I keep muting, and it just takes me a while to mute and unmute myself. Why would you use this Z threshold in a regressor instead of just using a classifier? Does that question? I don't quite understand the question.
I think I do understand it. The answer is we wouldn't. So we don't use Z in a regressor at all. We're thresholding the output of the regressor in order to build a classifier. Does that make sense?
Yeah, I think that's kind of.
Okay, great.
What is the point of the step function? I think so. So that comes back to what I was saying before. Think about it as a neuron firing or not firing, right? So when there's some default, when it reaches a certain amount of pressure at the input, then it generates an output and sends a signal down the line. And the step function is a mathematical representation of that physical phenomenon. Does that sound good to you?
Yeah, and it is essentially a way of creating something that's a binary classifier, essentially, from a continuous variable. So I want to move on. For bonus points, you can turn it into a logistic regression classifier, which we won't cover right now. And I've had this as a hands-on. We just did a single layer perceptron or SLP for a single data point. We're now going to do it for multiple data points, but I'd like us to do that together in the interest of time. Okay. So we're going to create 5 data points. Great. Now we're going to compute.
Hugo, you don't need to worry. In the interest of time, we've got lots of time. don't feel you need to rush through.
So for this notebook, we have around half an hour left. I definitely have half an hour left in me, and I'd like to cover the rest of this.
Okay.
Yeah. So what we're going to do is np dot once again, x, y plus b, and we'll actually see that, right. So this has built a regressor that's output 5 different results for 5 data points. The cool thing that has happened here is that our code, our NumPy code, has really just generalized from single data points to multiple data points. I think that's super cool. For those of you who kind of want to know about what's happening under the hood there, essentially what's happening, if you know a bit more linear algebra, is there's some form of matrix multiplication happening here. But we won't go into this right now. I think Dhavide will talk a bit more about this when he's building a feed-forward neural network. In
painful detail.
Yeah, fantastic. And what I encourage you to do after the fact is then that was for regression. You can then do it for classification, and then you can turn it into a logistic regression classifier again. The reason I'm not going to go through this now is because I'd love to get to multi-layer perceptrons. I'm going to scroll back up just to have a look at the one we've just done. We've essentially taken a single layer, which is the input layer, computed the weighted sum, and given it an output. Now, what we're going to do is we're going to generalize this, right, to using NumPy to having an input layer, then a hidden layer, then an output layer. Now, let me think about this. Do I want to ask a question? Besides that one, I do. Remember when we just had a single input layer, the number of weights we had were the number of inputs, plus 1 for the bias, of course, right? But if we have a hidden layer, how many weights do you think we need here? So let's say here we've got 4 inputs and 5 nodes in the hidden layer. Could in the chat, and no, there's no judgment here. I probably initially wouldn't have known how to answer this, but how many weights do you think we'll need with 4 inputs going into 5 nodes? If you could just write that in the chat. Oh, we got some great answers. My favorite answer so far is at least 4, because firstly, that's absolutely correct, and it's hedging your bets in terms of giving answers. I'm a huge fan of hedging. So the answer, a good question. Do we include bias? And somebody's written, yes, 20 excluding bias. So that's it. Exactly. So for each input, we want a weight for each node. So for input number 1, we want a weight going into that node. We want a weight going into that node, a weight going into that node. So for each input, we want a weight into each node. So for each input, we want 5 nodes. There are 4 inputs, so it's 4 times 20. Okay, great. So each of the 5 nodes in the first layer has 4 inputs, so it'll have a 4 times 5 array for weights. And we want this in an array form to make computation more straightforward. We're going to stick with the the other note is that the output layer has one node and 5 inputs. So we'll have a 5 times 1 array of weights. So we're going to stick with the toy e-commerce example from above. And this has 3 inputs, not 4. I found this image online here, and it had 4 inputs. So that's why we're using that. So as always, we first define our data, and then we're going to generate the weights we want. Okay, so the initial weights. Once again, we've already set our random number generator, but I'm gonna do it again in case. That's the thing. If you set a random number generator and then we execute cells in a different order, we can end up getting different results. Okay. I'm setting it at 42. If you know why, that's great. If you don't, check it out. So the first layer of weights, we want to be 3 inputs times 5 nodes. So we want a 3 times 5 array. The second layer, we want, so the output layer has 1 node, but 5 inputs from the hidden layer. So we want 5 by 1. The biases are going to be 1 by 5, 5 for each node in the hidden layer, and then 1 by 1 for the output. Okay. So I execute this cell. Now, if there are any questions after this, we can go through them, but I want to get through this first. Now we're building this multi-layer perceptron classifier. Okay, so for the first layer, I want to take X. So remember, I would have done np ... Now I'm going to do something pretty cool. I'm going to use this @ symbol, which essentially is np. It's actually the same, or a generalization of the dot product, which I think came out with Python 3.6 or maybe even 7, something like that. Anyway, it's awesome. So I'm going to do X @ W1 plus B1. So that will give the output Y1, which will be an array of all the values in the hidden layer. Then the second layer, I'm going to do, so that's going to be Y1 at W2, the second weights, plus B2. Now I want to output the thresholding. I want to get this right. So we used np.sign before. Now I'm going to use the sigmoid. So, and we'll see what a sigmoid is in a second. Actually, I'm going to open a new window and just show you a sigmoid for those who haven't seen it before. Sigmoid is this type of curve. Okay, so what we essentially do when building logistic regression, for example, we take a sigmoid function, and then if the value is less than a half, we call it one thing in terms of classifying, 0, for example. If it's greater than a half, it's 1. Okay, so we're going to do sigmoid. The output is Y2. We're going to see if it's less than 0.5. That will give us Booleans. I haven't defined sigmoid. I'm sorry. So I'm going to get us all to scroll up and copy and paste this. Okay. I apologize for this. So that's above hands-on SLP for many data points. And then I'm going to scroll down and paste it here. Okay. Now I'm going to re-execute this cell. But that it gives us a Boolean. It gives us a true. So what I want to do is just convert this to an integer. It gives us a 1. So what we've just built is a multi-layer perceptron for one input data point. Okay. So we've used the sigmoid function in the final layer. True perceptrons classically use a Heaviside step function, which you can look up. But generally, if you use other functions such as sigmoid, it's still called an MLP. I mentioned before, true perceptrons are generally classifiers, but MLPs in the more general sense can also be regressors. So the final thing is to build this multi-layer perceptron, we've just concatenated 2 linear operations. So going from here is a linear combination of all the inputs. then going to the output is also a linear combination. And for those of you who know a bit of linear algebra, this is actually still only a linear regression. And a lot of challenges in deep learning are nonlinear, so this won't be useful. So to deal with nonlinearities, we use activation functions, okay? And what that boils down to is in the outputs of each layer, we include slight nonlinearities. And as we build more and more layers, it captures more and more nonlinearities, okay? So historically, than, it's written tan-h, but pronounced than for some reason, probably because tan-h is 2 syllables, has been a popular activation function. We'll see it below. We've seen the sigmoid function. A very popular one these days and quite useful one is the ReLU, which is the rectified linear unit, which is defined. It'll be equal to x if x is greater than 0, and it'll be equal to 0 otherwise. So I'm just going to define that there. And I'm going to plot them all and then just give you a few rules of thumb. So this is, I'm going to plot than. Alrighty then. So I haven't imported matplotlib now because my session timed out. Okay. And I'm also going to import Seaborn. You don't necessarily have to do this, but your plots will look slightly different and set what our plots will look like. Okay, great. So let's have a look at this. We see this is the sigmoid that we've discussed. This is ReLU. So it's 0 if x is less than 0, and it's equal to x otherwise. And this is than, which is inverse tan from your junior high calculus days or middle school calculus days, presumably. Now, I'm not going to dive into which ones to use when. I can tell you that ReLU has been incredibly successful for something that is piecewise linear in deep learning. For rules of thumb, think about the output layer. If you want your output in a regressor to be squished between 0 and 1, use sigmoid. If the output needs to be positive only, use ReLU. If it needs to be between -1 and 1, I'd use than. These rules of thumb, I had a colleague and friend of Dhavide of mine, Eric Ma, have a look at some of these notebooks, and he suggested thinking about these heuristics. And so I just want to give a shout out to Eric for that as well. So I think as a hands-on now, this is a good question. Would we like to do a hands-on of adding activation functions to the multi-layer perceptron, or move on to deeper networks?
There's nothing in the chat yet.
Let's take 5 minutes.
Let's take a poll. How do we do the poll thing again? Alex did that last time. Hands-on. I think the hands-on is coming deeper.
For the poll, you can click at the bottom of the screen. There's a poll button and do create poll, and then type in your question and your choices.
I don't see the poll button.
Next to ask a question, or maybe I'm the only person who can do this.
Unanswered questions, people. I don't see it.
Okay, so
let's just. I suggest we do a hands-on because it'll take 5 minutes.
Okay.
Why don't we get everyone to do the hands-on of adding activation functions? And what I'd ask is that you use ReLU activation functions internally. Within the hidden layer, and then maybe a threshold function at the end, something like that. So let's take 5 minutes for that. To generate the weights and biases, just recall it's 5 data points, 1 hidden layer with 8 nodes. And so you'll do something similar to what I did previously, and then you'll do the computation of the first layer and the second layer. So while we'll take five 5-10 minutes to do that. And while we're doing that, I'm just going to stretch my back. Hi, everyone. I'm back. Can you hear me?
Yes, we can hear you.
Yeah.
Great. So what I'd like to do is just write the code that that I think is good.
Quick question, Hugo. While you're doing that, can you explain the size parameter, please? And we're not seeing your screen yet at the moment.
Oh, that's on me. Blankety blank. Okay. Let me remember how to. I love there was a comment. Oh, that's actually me. Hi, everyone. That was unintentional. This is me lying down. Great to see you. Okay, I'm going to toggle that off and actually share my screen this time. Application window. Oh, good Lord. What? I'm sharing my email now?
Yes, you probably want to hide that.
This is really bad. Good gracious me. The only excuse is that it's nearly 2 a.m.
Oh man, God love you, man. Thank you for
Absolutely.
doing it. We're okay.
Oh, it's such a pleasure. This is a lot of fun, and it actually isn't the weirdest timing I've had. There was one webinar that I had to get up at 3 a.m. for when I was in government mandated military enforced quarantine here. So the size parameter, that's a great question. I'll talk us through it as we do it. Okay. So here we have 3 features going into 8 nodes. Okay. So remember, we want how many weights do we want then? We want 3 times 8, okay? And the way to do that is to create an array, which is the dimensions are actually 3 by 8. Does that make sense? And similarly, going from the hidden layer to the output goes from 8 nodes to 1 output node. So we want 8 by 1 there. Okay. Now, with the bias, the first bias, we want 1 for each node in the hidden layer. So it's 1 by how many nodes in the hidden layer? 8. And then finally, we want one bias for the final node. So it's going to be 1 by 1. And the location there, I'm not sure why I did that, but that sets the mean of this normal distribution, and it may have been purely to get numbers that make a bit more sense. Okay. So we do something similar to what we did before. We take X and we do the dot product with. I can hear you typing, Dhavide.
Sorry, I keep forgetting to.
That's great. I'd almost be concerned if I didn't at some point. I like the gag we have going on. So then I asked us to use ReLU for the activation function internally. So, and then I'm going to print the output. Ooh, a sec. I probably should run that. No kernel, of course. Now, I will restart the kernel. But instead of trying to import NumPy and then figuring out I wanted to import other stuff, if you bear with me, I'm going to scroll all the way to the top. And not all the way, and do my first cell of imports, okay? And then I'm going to scroll back down. Okay. So we're going to set X. Now we're going to set all the weights and biases. We're going to do this first computation. Oh, of course. Okay. So this is... Okay, so I've now defined ReLU again, and I apologize if you're jumping around cells in order to do this. This is some Jupyter binder foo, which occasionally one needs to do. So I'll execute that again. And we'll see, this is outputting the results of the hidden layer, essentially. So in fact, right now, the joke is it's not so hidden, but generally it is. So what we're going to do now is we're going to take, let me get this right. Yep, the output of the hidden layer, multiply it by the weights, add these biases, and then do np.sign as a thresholding function here. See, these are the results that it spits out, okay? And notice, because of the weights and the biases, it gives us all the same results, and that's probably something we don't want. And if we were to train using gradient descent or back propagation, we'd see that we hopefully get different results if that's what we want, if that's what the labels actually are. So the next section is on building deeper networks. Now, I'm not going to do this now. It's in the instructor notebook, and I'll leave it as an exercise. One thing I'll note is as we build deeper and deeper networks, so this is now one with 4 hidden layers in which each layer has 3 nodes. Building all these weight arrays becomes quite cumbersome. So we can leverage one of my favorite Python objects in the world, which is the dictionary. We can store the weights in dictionaries where the names of, the set of weights we're thinking about are the keys, and the weights themselves are the values. But we won't go into this too much now, but that's an exercise for the reader and in the instructor notebook. I just wanted to give a note on representation learning. If we're talking about building deeper and deeper networks with more and more hidden layers, I'd like to mention that one of the most important subtasks of machine learning is feature engineering. So this is, constructing features that make sense and make good predictions. Now, a nice aspect of deep learning is that neural networks tend to learn features implicitly. So, for example, the more layers a neural network has, the more complex features it can recognize. And as I wrote here, early layers can start to identify edges in images, then combinations of edges, then corners, then more complex features, etc. And I've included a resource here, but if you check out representation learning, you'll see a lot of cool stuff. So we've just gone through forward propagation. And so I think you should all give yourselves a pat on the back for being able to build simple neural networks and using them to make predictions on data solely using NumPy. So congratulations to everyone.
So Hugo, we're just at the top of the hour now.
Yeah.
If you, you can hand over to me if you want to go to sleep. You can keep going and finish this notebook. I will leave that choice up to you.
I appreciate that. Let me scroll through and see.
There's not a lot left, I don't think, right?
No. Yeah. Why don't I see how I go through a couple of code cells, and then if I find myself, what I don't want to do is bore myself to sleep. And that's half joking, of course. I'll go through a couple of cells and explain gradient descent, and then hand it over if that works for you, Dhavide.
Absolutely. I will be doing things differently because I'll be teaching solo, so I'll have to figure out how to manage the chat and questions differently. So I'll try and figure that out. But you do what you need to do.
Thank you so much. I appreciate it dearly. So, as I mentioned before, backpropagation, also called backprop, is the algorithm used to optimize the weights of neural networks, okay? But before jumping into backprop, I just want to talk about gradient descent and how that can be used to optimize the weights of perceptrons. So, I can hear you typing, Dhavide.
Yeah, I know.
I'm glad you didn't apologize that time. So essentially, when we do forward prop, we get some results. But if it's training data, we already have a label to that data. So we can compute the error right? Between what our forward prop gives us, what our forward propagation gives us, and what we know the values are. And so we can visualize the error as being kind of in this landscape where if our error is really high, then we want to change our weights in order to climb down to reduce the error, okay? So we use this gradient descent. We figure out some sort of gradient or slope in order to move down this landscape in order to reduce the error. And we do that by changing the weights. Then we do another forward propagation to see if we've improved our predictions, and we iterate, okay? So I want to give an example of gradient descent with the single layer perceptron now, okay? So let's now, I just want to write, this is our single layer perceptron before. I just want to write a single layer perceptron function because we've actually written out the code so many times. Of course, golden rule, if you write code 3 times, write a function, okay? So this is going to be taking arguments x, the data, w, the weights, b, the bias. So x at w, so this is the dot product plus b, and I'm defining that function, returning the result, okay? So now let's do this function to do one forward pass for this single data point, okay? Once again, we're going to initialize our weights using np.random normal. We have 3 inputs, so the number of weights is going to be size equal 3. Now, y hat, which is the result, we know what the target variable is. It should be 10, okay? So we're going to now compute SLP for x, w, and b. What have I done there? Can anyone see the mistake I've made? Oh, I've been cheeky, haven't I? I've got four inputs here. So I need 4 weights. So if I change that to size equal to 4, it should be okay. Okay, good. So the target variable is 10. These weights have output 0.3. So it has a bit of work to do. So to do gradient descent, what happens is, and I'm using words here, not a lot of equations, we must shift each weight slightly in a direction that will make the prediction better. So what we do is we look at how bad the prediction was, which is going to be y hat minus y. We take the dot product with the relevant x's, because we want to weight it with respect to the x's, and we multiply by something called the learning rate. And we set this, okay? So essentially, I'm going to scroll back up to the gradient descent here. What this does, doing y hat minus y, taking the dot product with x, will allow us to climb down the gradient, hopefully, okay? Then the learning rate will tell us how far to go in that direction. So that is exactly what I've done here. So we do the forward prop, we calculate the y hat, we set the learning rate, then the change in the weight is going to be delta w, which is the learning rate times the dot product of y hat minus y with x. And because we only got one data point here, the dot product is just the product. Similarly with delta, the change in the bias. Now let me get this right. I actually have messed this up slightly. We want to change w. We want to minus the delta. So if the prediction is larger than the actual value, we want to reduce the weight slightly, okay? And similarly with the bias, and there's one thing, it's a quirk of doing array operations. We want to reshape this slightly, okay? So this is one round of forward propagation, followed by one round of gradient descent to change them, okay? Now, there is a hands-on here, but I'm actually going to do this now. And then
so why are we dividing by 100?
Yeah, where have we done? Oh, yeah. So I divided by 100 here, essentially it's a proxy for normal. That's a really good question. It's a proxy for normalizing the data set. Generally, when you have data that goes over a variety of ranges, you want to shrink it down to between 0 and 1. So, for example, if you have an image with pixel values between 0 and 255 or whatever it is, you'll normalize to get it between 0 and 1. And this is a proxy for doing that. And what it means is that when we perform gradient descent, it hopefully won't blow out by having too large values that kind of jump around the gradient landscape. Does that make sense?
Yeah, I think so.
Okay.
Can you explain the signs on W and B change again?
Yes. Yeah, I hope I can. Okay, so Y is the actual value. Y hat is what we've predicted, okay? So if we've predicted something larger, first actually notice if Y hat is equal to Y, the prediction is exactly the target value so that the delta is 0. So we don't change anything at all. So that's cool. That's a sanity check, right? So if what we've predicted is larger than the actual value, then reducing the weight will reduce this Y hat and hopefully bring it closer. It can overshoot. It can reduce it too much. So if this is positive, we want to subtract it from W is the point, as opposed to add it. So I hope that clarifies that for you. So I think I have this as a hands-on, but I'd like to walk you through it. And then the following hands-on, I think you can actually do after the fact so that we can move on. But let's do this together. I just want to state that what we're going to do is we're going to do rounds of forward propagation and then rounds of gradient descent to update the weights. And note that we're actually updating all the weights simultaneously using gradient descent.
Okay, hang on, Hugo. There's a bunch of questions here. Why are you multiplying by the input x? I think that's got to do with multiplying on the left. Is that correct?
Yeah.
Why reshape? And why are you multiplying? And since y equals 10, why not add? Sorry, I'm just trying to figure out what these were in reference to.
Absolutely. So the reshape is literally, if I don't do that, yeah, I get a miss. Okay. I'll answer the reshape first. The answer is that NumPy wants, what have I done? Let me go back, do this. Yep, NumPy wants this in a particular shape for me to be able to do future NumPy operations. So that's why I'm reshaping it, essentially. I can't quite speak to which specific ones currently. The answer to why I'm multiplying by x is that essentially this is, I'm interested in how many people want me to answer this actually, because it is quite nuanced. I wonder, actually, I think Sebastian probably has the best explanation of this. I may have linked to this in the notebook. I'm scrolling through this. This is literally the original rule for perceptrons to do this calculation. And what it does is it weights the change I'm overloading the term weight here. It weights the change in each weight update with respect to the input value, so that it respects what we're putting in, essentially. So what it will do is, I'll go back now. If we didn't multiply by X, it would update all the weights the same amount, whereas we actually want to update them differently with respect to what we're putting in there. And if that explanation doesn't quite suffice, in the interest of time, I will move on, because I think there are probably more important things.
Yeah.
Because this of course is a really nice thing to see now. Once we do forward propagation and then gradient descent and go back and forth, we'll see the error get closer and closer to zero. Okay, so I originally wrote, in this case, a round of forward prop followed by a round of gradient descent updating the weights is called an epoch. You'll also hear it called epic through a lot of the deep learning community. I call it epoch for whatever reason. Maybe because that's how you say that word generally, from like where I come from anyway. But more generally, an epoch is one pass over the entire data set, not just one round of forward prop and gradient descent. So for example, you could have 2,000 data points and a batch size of 50. So what that means is that each round of forward prop and gradient descent, or forward prop and back prop, which we'll see, you use 50 each time you do that. Then you would have 40 iterations before you hit one epoch. There we go. Okay, so let's do this now. We're going to do a round of forward prop. So we've defined the target value for this one data point, which is 0.1. Then a list for the list of errors. So y hat is the output. Okay, so that's going to be SLP X WB. Okay, then I want to append the error to diff. So this is a list, and lists have this nice append method. Append. So I suppose I want to append y hat minus y. Does that look right? And then,
yeah, that looks good to me.
What I'm going to do is I'm going to copy and paste the good old copy and paste my changes. And then I'm going to do the same with these two. Yep. Now, so we're now doing, let's talk through this before we plot it. We're doing 30 epochs where we do the prediction once, and then we go back and adjust the weights using gradient descent. We're going to do that 30 times. And then what we're going to do is plot the errors as a function of how many times we do these epochs. So hopefully we'll see. Okay, great. So, yeah, just a sec. Okay, that isn't quite working. Anyway, the display challenges aside, what we see is that what started off as an error up here slowly, or at some rate, converges to something quite close to zero. So this is a sanity check that as we this is the training process, right? Of doing forward propagation followed by gradient descent to figure out the best weights, which are our hyperparameters, in order to build this neural network, this model. Now, a hands-on that I won't do is doing the same for many data points. I'll just state that when you have many data points, the difference in the result, the difference between the prediction and the actual result isn't a single metric because you've got many data points, but we use the dot product of the difference with itself divided by the number of data points, which is a measure of distance. And this is actually what is commonly called the mean squared error, which you may know. So what I'm going to do now is I'm going to chat. We've talked about gradient descent. Backpropagation is what we really want to use. Gradient descent is a nice introduction to backpropagation.
So Hugo, if you're actually if you're fading, I'm covering this more in great detail in the next notebook.
Fantastic.
So
so what I'll do is I'll just say maybe a few more words about backprop, and I don't want people to be distracted by the math in this, or the maths, as Dhavide and I. Oh, do you say maths, Dhavide, or math?
I grew up in Canada, so I actually say math.
Okay. The mathematics, let's say. So to ignore all the mathematics here, all I want to say is that as we saw in forward propagation, the input data flows through the network to give us an output. In gradient descent, we saw all the weights updated at the same time. What happens in backprop, as Dhavide will tell you in great detail, is we see the error terms flow back through the neural network in order to update the weights, not at the same time, but we update the ones closest to the output first, and then it flows through that way. So I think that is probably a fantastic point at which to hand over the torch to Dhavide. Does that sound good to you, Dhavide?
Yeah, I think let me I'm gonna have to start up my binder and okay, so let me turn on my camera so I can look at you. I'm fortunately my back is in good shape. Thank you so much, Hugo.
Thank you, Dhavide.
You take it easy, big guy. Get some rest. We'll catch up later. And
I appreciate it.
And everyone just everyone's giving you the love in the chat. So you go get some rest.
Fantastic. Thank you so much, Dhavide. Thank you, everyone. And I just wanted to say once again, please do give us feedback afterwards and give us some pull requests as well, whatever you find interesting and would like to see. Enjoy the rest of the session. All right. Thanks, everyone.
Okay. Yeah. Cheers, man. All right. So I want to ask one thing from folks here. Now, I noticed that there's things in the chat and there's things in the questions and answers. And since Tanya will be here running interference, so she can maybe answer some of the things in the chat. But but I noticed we haven't actually been using the upvote features on the question and answers. So what can happen? What I'm going to recommend is that when you get a particular question that you want to ask, you can do quick and dirty ones sort of in the chat. When you've got something you want to articulate a little bit more clearly, put it in the questions and answers, and I will. And then if people can upvote those ones, then I'll take a break every couple of minutes, take a look at it, and then I'll try and address the ones that have the most upvotes. And now I have to find where the link is again to the GitHub. Can someone actually just paste that in the chat for me, just so that because I've lost my tabs here.
There you go. Just sent it in.
Thank you, Alex.
Mm-hmm.
All right. All right. And let me share my screen for a minute while I start up my binder. Yeah, I'm going to launch a binder because I know what that is. And let me share my screen. How do we do that again? Sorry.
Hover over your own.
I know. I got it. I'm sorry. I'm just speaking out loud. Okay. Thank you, everyone, for coming today. Okay, my binder is starting up. Let me just show you something. All right. I want to try and get into the PyTorch stuff as quickly as possible, but there's two notebooks here, and we can go through these in a number of different ways. But I want to show you PyTorch.org is sort of where there is a lot of information. There's tutorials
Dhavide?
here. Yeah.
Sorry to interrupt. People are asking for a short break
absolutely.
between notebooks.
Absolutely. Yeah, let's take 5.
Minutes. 5 minutes? Okay.
Yeah, absolutely. My apologies. Thank you, Alex.
No problem. No need for a poll. See you in 5 minutes.
Okay, folks. I'll just give it another minute. I'll let everyone, and then if you'll want to come back, will these tutorials... All right. Hello, everyone. Welcome back. This is Dhavide. I'll just sort of slowly come back with some sort of minor administrative announcements. So we've got about another hour and a half left. And I don't know why I'm exhausted, even though Hugo was doing all that work. But that's okay. I will earn my keep here. So my name is Dhavide Aruliah. I'm a data scientist. Well, I'm an applied mathematician at heart, really, computer scientist. And you'll see that from my notebooks. So as I said, I'm going to suggest that we try and upvote questions. I don't know how, someone suggested I mark all of these as red, and I don't quite know how to do that.
I'm trying. I'm taking care of that right now by clicking start answering, stop answering. So the timestamp won't really make sense, but this way we'll keep them on the entered side. Yeah.
Oh, okay. Could we take a step back from the neural networks? How is what we're doing with weight stop projects in the notebook relate exactly to what we're trying to predict? Yeah, that's a good question. Okay. Let me see if I can answer that in a sensible manner. I'll get to that notebook in a second. Let me just talk a little bit first, a general question about PyTorch, because there's been a few things about that I've also been asked, and I'll come into that. So PyTorch versus TensorFlow and Keras. So PyTorch is a framework for working with neural networks that came out of Facebook. It's an open source project. In fact, at my company at QuantSight, we're associated with people that work on that. And TensorFlow is the sort of the Google product, which is older. And Keras is a module built on top of TensorFlow to make it easier to use. So PyTorch has a module called PyTorch.nn, which is sort of like the version of Keras for PyTorch. Which you would want to use is it's kind of a Vim Emacs kind of question in some sense. I think there is an advantage of a framework that comes later. Since PyTorch was later, they managed to make some design decisions that TensorFlow did not. So that actually ended up being an advantage in a lot of contexts. So for instance, PyTorch admits what's called dynamic computational task graphs, which means that the network can be updated dynamically throughout computations in the middle of some workflow, whereas in TensorFlow it needs to be done a different way, and that's a design decision that went early on into the building of the software. It doesn't really matter what that means, but that's one thing that they point out heavily on PyTorch's website. Let me share my screen, and I think you're seeing it now. Okay. So this is pytorch.org. So there's a lot of resources here that you can look at. And I think so getting started is how you would actually install it on your system, right? So you can sort of see, sorry, I know I'm scrolling quickly here. This is just various ways, you can select different options, whether or not you've got GPU. Wait a minute, where is that down here? None. Here we are. Like if none is whether or not you've got CUDA, and you can get instructions on how to install it on your system. And also appropriate for your operating system as well, right? So it's actually kind of a nice interface. The tutorials, there's some really good tutorials, but I actually think when Hugo and I started, it's one of the things I was looking at is we were thinking, okay, what are we going to expect the prerequisites for this are? So at SciPy, I was thinking, I'm thinking that people are scientists generally, so we can count on a certain amount of quantitative expertise and maybe a little bit of software development more than we might do in more business-focused kind of environments. But one thing I did find is if you look at a lot of these tutorials, like the 60-minute blitz is a really good one, and it's actually really nice and simple. But I think also there is a count when you look at these things. They count on a certain understanding of what a vocabulary of neural networks, and that's so I think our goal in some parts. So there's this one here, learning PyTorch with examples, by Justin Johnson. And I kind of have modeled what I was trying to do on this, but fleshing it out and doing a little bit more in detail. So starting with a NumPy-based neural network and then converting it to something in PyTorch incrementally. So that third notebook that we've got is actually based a lot on this. But what did I want to tell you now? Okay. So for my next, so the next bit, the next hour and a half, what we'll do, I'll go into the notebooks here, and there's two more notebooks, the instructor deep learning, this student deep learning, and I'm going to open up the instructor one in the background just in case, because I have a feeling I'll minimize that window a bit. Everyone can see this. Let me quickly go back and check the questions at the moment. Okay, so again, feel free to put questions in here. Feel free to upvote them. I'll try and check back here every 5 or 10 minutes just to make sure that I'm on track with everyone.
Your helper watched for the questions.
Okay, that's great. Yeah, it's Tanya. Is that correct?
No, Alex is here. I asked Tanya if she wanted to come online, but Tanya, if you want to come online, just ping me on Slack and I'll make that happen. Okay.
So Alex is on top of this. Okay. So let me sort of take
one more thing.
Yes.
One more thing, Dhavide. Can you make the font size a little larger?
You got it. Thank you. Let's say increase. Is this going to work? No, it's not. Okay, I'll just use the Control+. There we go. Okay, that's good enough. All right. So now I have to apologize a little bit. I'm an applied mathematician by training, so my machine is frozen. Oh, I see. There we go. What has happened there? There's some latency with this Colab thing. Okay, there it is. So I'm an applied mathematician by training, which means that I've put in some pretty hairy math in here because it's difficult to do otherwise. And ultimately, I found it really, I had to do a bit of reviewing. I was trying to fill in some of my own gaps, basically, about neural network and backpropagation to understand it. And I'll explain the big broad strokes of it as best I can. But my notebook has a lot of math in it for those that want to read it. Yeah. Sorry, was that someone? Okay. And but one of the things that is tricky, so I've used a book by Michael Nielsen. Pity Hugo has left because Michael is another Australian. So he might appreciate this. This is a freely available book. It's all online. It is beautifully written. And he has done this very, very artful job of using sort of the bare minimum amount of math in the second chapter, but there's a lot of intuition, and you can read it all online. It's actually not that long. I actually sat down the other day while I was preparing this to actually work through this, and I was just impressed at how much how beautifully well written it is, and how it's actually well worth reading through if you want to. So my goal a lot of the time when I'm teaching is to figure out a way to get students to the point, to get learners to the point where they can pose their own questions and figure out how to answer them themselves. So I think the challenge when you look at, when I was looking at this PyTorch website, right? When I look at this particular tutorial, it launches out immediately into this NumPy example of a neural network trained with steepest gradient, steepest descent. And so if you're not familiar with it, my hope is that at the end of today, you'll actually have a really good sense of what's going on there. There are some challenges. My notation is a little different than his because I've done it the other way. And again, and let me come back to, I think it was Catherine's question that I didn't answer before, relating all of this stuff about neural networks and these funny diagrams and these arrows and circles. How does this relate to a problem that I want to solve? So one of the things you could look at in this one here is this is a neural network with 3 input neurons and 2 output neurons. So this is some kind of a 2-class category classification system. So you have some inputs that you're feeding in on the left, and some magic occurs within the network through a series of functions that are determined by a bunch of weights and biases and activation functions. And at the end, some numbers get computed and are put in at the right-hand side in this output, which determine which class, and depending on which neuron fires at the end there, that determines what the output is of the network. So this is a mathematical way, a graphical and mathematical way of representing all of these ideas. Now, one of the things that is, the way this has been written is a little bit backwards. So I'm using this notation WL to refer the weight matrix associated with the ELF layer of the network, and BL to be the bias vector associated with the ELF layer of the network. And what this means is then we multiply the outputs from one layer by the weight matrix and add the bias, and that translates translates information from one layer to the next. But then there's this notation with superscripts and subscripts, which is really hairy, right? W243 is the weight that tells you how the hang on a minute, the 4th neuron in layer 2 is weighted in transmitting information to the 2nd neuron in layer 3. So the superscript refers to which layer, and this layer is 1, 2, 3. And the subscripts refer to which neuron in which layer. And so it's kind of counterintuitive because the rightmost index actually refers to the leftmost layer, the left layer in this notation. And the reason why that is done comes down to the way that we the way that we actually do the matrix multiplication. We'll see that later on in this notebook. It's a hairy detail. It's an annoying detail, but it's something that if we don't get right, we can't get things to work. Okay, so let's try and do some things. If I find that things are, I want to try and make sure we get through a good chunk of them. I don't think we'll get through all of it, at least not in the sort of a traditional way. Oh, I have not. This has already been executed. I thought that. Oh, you know what? Let me clear my kernel and clear all outputs, just because I like to do that when I'm running a new notebook. Okay. So I've laid these all out basically as exercises, but I think in the depending on how fast we're going, we can skip through some and paste them directly. Oh, I know what I'm doing. I'm looking at the instructor notebook. That's what I'm doing wrong. All right, so here we go. We can work through these. So first thing I want to do is associated with each of these layers, with our network, there are layers, there are weights, and there are biases. And the weights are matrices where the dimensions relate to the two. So the weights are associated with the arrows and the biases, and the circles are related with the actual layers. So I want to write a function that just generates a model that we will store in a dictionary. And the reason I'm doing this is kind of the work that has gone on in the design of a library like PyTorch, in the design of a library like TensorFlow. So we're going to see a little bit of this background stuff today, so that when you're using PyTorch in the future, you'll actually have an understanding of all the work of how this fits together. So we're going to make a dictionary that has 3 keys and 3 values and with values associated. So one is called the number of layers in the network. One is a list of the weight matrices, another is the list of the biases. So, and the way that we set it up is we have a list of dimensions. So dimensions is going to be a list that tells us, this is what I would call a 2-layer network. The input layer, we just think of as being the inputs. We don't count that as a layer. So we've got a list of length 3. So we'll say L plus 1, capital L plus 1 is the length of dimensions. L is the length of the number of layers. And I apologize, this is going to be completely inconsistent between every single post, every single book you read, every single article. It's impossible to make a uniform notation on these. And so it's a difficult thing that you have to get used to, not only when you're reading papers, but also when you're using software. So I'm going to write a function that's called initialize model. I give it this list. It returns a dictionary. And when I run this loop, it prints out there's some details. So my dictionary has 2 layers, basically, that correspond to 784, 15, and 10. So the weight matrix W1 has shape 15 by 784. So that's the 2nd layer dimension and the 1st layer dimension. The shape of the bias is 15 by 1. For the 2nd layer, the shape of the weight matrix is 10 by 15. And the shape of the bias vector is 10 by 1. So notice I've actually made these explicitly column vectors. So all I'm going to do is I'm going to use calls to like numpy.random to generate these matrices, and let's just fill in something to do this. So let's take a few minutes and see if you can write this out. If this is a clear enough specification, we'll make sure we get it working. I'll look and see if there's any questions right now. Okay. Let me see. Does 74 represent the batch size in this case? No. Oops, let me answer that question. No, that's the dimension of the input. Actually, can I comment that again? Actually, in this instance, it would be 28 times 28. All right, I'm going to share my screen. So just as context, maybe let me just see if this is actually... If anyone is finished, can you just put finished into the chat just so I get an idea? Oh. Okay, great. Okay, so just answering Shubham's question here, Prachi's question there. So this is an interesting example. What I've chosen here, I'm sharing my screen. This is called the MNIST digit classification data set. And what is interesting about this funny example here that came from Justin Johnson's here, he actually chose an example which has 1,000. So that would be, I guess, oh, wait a minute, 1,000 is not I don't know why he chose 1,000. That's not a perfect square. It's a perfect cube. Yeah, that's interesting. And 10 is the output. So this is really, so I thought that maybe I would think of this as the digit classification. So there are 10 different digits, the numbers from 0 to 9. The MNIST data set refers to a bunch of images of handwritten digits that were collected from postal workers and high school kids in the 1990s. So they were scanned into 28 by 28 in various other images. And so we can use those as a benchmark, and I had intended to get that tied into this, and I didn't, and I apologize for that. So we're still using random data, but the idea is you have with each, the inputs would be an image that has been reshaped to be a vector. So a 28 by 28 image can be reshaped to a 784 by 1 column vector. And they would be labeled from 0 to 9 corresponding to which digit that's a representation of. So the reason why I chose this example here is this would correspond to an example network we would use for the dimensions where we're taking in vectors that have been reshaped images, we're mapping them to an input layer, a hidden layer of length 15, and then outputting those to some layer of length 10, which is which is ideally probabilities of whether or not things are the digits from 0 to 0 to 9, right? So you forgive me, I'm not going to try and code these up because I want to try and get these out. So I know that's, maybe bad pedagogy, but so I want to point out a few things about this that's kind of interesting, right? So the way that I have written, that I've set this up here, right now, if I copy this and actually do what I've got up here, I think this should give me the right results, right? sorry, let me scroll up a bit. Model equals initialize model dimensions. Right, and actually let's do print model.keys. Right, so it's the key thing is I had to do the random generation, and I had to extract the entries of the list dimensions in the correct order. Right, so I had to do dimensions L+1, comma dimensions L when I'm generating these. Right, so that so if I run that loop now, what I can see. Oops. Let me get rid of that line there. Right, and I get what I want. So it's a 15 by 784 matrix and a 15 by 1 vector. Right, and notice I've made these two-dimensional arrays. Even the column vector B1. NumPy and MATLAB, if you've ever worked with it, can be a little bit particular about that kind of stuff. So it can be very important to get these things right when you're doing work. So we've got something that just makes a model, which is a representation of all of the data that we need to store for this neural network, right? So I've got, in principle, the weight matrices and biases stored as random matrices and vectors associated with the transitions between each layer. What I don't have yet is activation functions. So for the present version, what I'm going to do is I'm going to implement a choice of activation function. And I'm going to just use the sigmoid logistic, which is all, and I'm going to use, for the loss function, I'm going to use the quadratic, the L2 norm loss quadratic. I just want to point out, I've written some code here to implement the logistic a little bit more numerically elegantly. So for instance, you can, if you do some manipulation, just a little bit of algebra, you can figure out that the sigma of x, you can write it as 1 plus e to the minus x for positive values of x, and 1 minus 1 over 1 plus e to the x for negative values of x. Any idea why I would want to do that? Can you step through the initialize model function again? Sure. Let me quickly do that. Sorry. So what I did is, first of all, I just received this list of dimensions. I initialized two empty lists. I took the length of dimensions and I subtracted one, and I'm just calling that capital L. Just for my bookkeeping, I want to call L the number of layers, and then excluding the input layer, because that doesn't actually, because we have one more. If we include that, then we have one more layer. Then we have number of parameters to compute. So then I just loop over lowercase l, and I generate random matrices and random vectors that are of the appropriate size, so that when I do an appropriate linear transformation, an affine transformation, a multiplication wx plus b, it will give us the result for the next layer that we need. So, and I appended those as I stepped through this loop. So at the end, then what I did is I used a call and I constructed my dictionary that has the appropriate keys and the appropriate values. So these will be changed using this particular constructor of the dict function in Python. Those will be converted to strings, the weights, biases, and layers there. So the next thing we want to do is we want to implement the function sigma, and also what I'm calling here script E. Now, I'm using the math because it helps me think. What I had to do the math in order to make sure that I got this worked when I was debugging it. If I don't do the math, I can't write a program that works. I like to turn the math into a program that works. And so I know that isn't everybody's cup of tea, and some people don't even like tea. But yes, thank you, Christine. Overflow. The question I asked a few minutes ago: why write sigma like this? And the answer is it is more robust for numerical evaluation, right? If I have positive values of x, e to the minus x is always going to be between 0 and 1. If I have negative values of x, e to the x is always going to be between 0 and 1. If I don't do that, then I can have very large values, and I can end up with some numerical stability problems in evaluating it. The other thing to point out is the derivative of the sigma function is given in terms of the sigma function itself, sigma times 1 minus sigma. That's an exercise in calculus. I'm going to assume at SciPy, even if you can figure that out if you need to, but it's not an interesting fact. You can take that as given. This notation, I probably shouldn't use this, but this is the Euclidean norm squared of y hat minus y. So we'll think of this as being the loss function, which is the thing we're going to minimize, which is the cost, basically. If you think of, if I give my training input, I give it into my feed-forward neural network, my multi-layer perceptron, whatever I want to call that. I'm sorry, I'm using these two terms that are often used synonymously, but not quite, sometimes minorly different. So y hat is the output prediction from my training data. Y is the actual supposed labels that I should be getting for the output. So the difference of those is how much they misfit. If I take that and I square those component y's and add those together, I take the Euclidean norm, or I square the Euclidean norm. This is the quadratic mean square error. Sometimes it's called. I'll call that E, or which maybe I can think of as error or energy. The gradient with respect to the parameter y hat is going to just be the vector y minus the vector y. Vector y hat minus the vector y. So these actually I will fill in on the fly because it's easy. I didn't want to. This thing here is a way of writing that piecewise function elegantly in NumPy. It's a nice NumPy trick, right? So, but the nice thing is I can do these fairly quickly. Sigma of x multiplied by 1 minus sigma of x. Notice these are vectorized functions. Whoops, I misspelled sigma. Right, so what that means is if I give it a vector as input, right, if I do something like z is equal to numpy dot array 1, 2, 3 dot reshape minus 1, 1, print z, comma sigma of z, comma sigma prime of z. What I notice is this reshape command, because I was reshaping a one-dimensional, I basically left out the leading dimension. And as long as I put in all of the dimensions except for 1, I can use -1, and NumPy will figure out what that missing dimension is. So I figured out I was working with a 3-dimensional vector, and it reshaped it as a column vector. The reason I want it reshaped as a column vector is because that will be consistent with the way that I want to write out my affine mappings, my matrix vector products, when I'm doing the transformations, when I'm in between the layers of the neural network. So it's an annoying detail, right? And it's inconsistent actually with what Hugo wrote in his slides, right? Because I want to do W times X plus B, not x times w plus b, which is what Hugo wrote in his slides. And maybe you guys can say, oh, couldn't you guys get your act together and be consistent? But I would actually argue that there is value in actually being able to get this detail right, because you're going to have to do this to get software to work correctly. You have to be able to read the documentation of the software, and these kinds of details, as much as it is a pain in the neck, is something that foils us up and gets confusing. And you know, we can get it right if easily enough. So this is sigma of z is also, anyway, it's vectorized. So I gave it a vector input. It gave me a vector output element by computing element wise. And so is sigma prime. Okay, let me just quick to see if anyone asks any questions. You can set the seed if you like, Douglas. I haven't, it doesn't really matter. Oh, sorry, what is the zip function? The zip function, Scott, that combines, Tanya has answered that for me. Oh, wonderful. Thank you, Tanya. Okay, great. Let me quickly put in the loss here. I'm going to write it out in a very inelegant way. I'll say y hat minus y, and I will do it like this: numpy dot square dot sum, right? And then loss prime is just simply, oh, and I forgot I was going to put a factor of 0.5 here. That's not actually mandatory. But the only reason you want to do that is, and what would this be? This is just y hat minus y, right? And let me just check that works. If I do I'm not going to do an example of that. That's simple enough that we can figure that out. Okay. So again, I'm using a little bit of this hairy notation, but I need to do this so I make sure that I can write the function and do this. Again, I'm a mathematician, so I think about these things in a particular way. So let me just take a quick poll. I can leave this to you guys to see if you can figure out how to write this function, and we can take 5 minutes and you can do that, or I can quickly cut and paste it in. Can I just see what that is? What people's are? +1 to, or +1 in the chat.
I'm writing a poll right now.
Writing a poll. Thank you, Alex. So the choice is doing the exercise. +1 is doing the exercise. I think also.
Poll should be visible now.
All right, there will be a poll. Oh, here we are. Good. Yeah, vote. Right, the function. Oh, you guys are. Oh, this 50-50 split.
So it sounds like it's your choice.
Okay, no, it looks like the pasting the answer is slightly winning now.
Yes.
I tell you what, I'm gonna. Okay, it's winning larger. All right. Okay.
Let me know when you're satisfied with the state.
Yeah, I think I'm going to paste in. Okay. Sorry, guys. Like, it's. You know, I want to try and it's actually not that complicated. It's actually fairly simple in terms of the structure of Python. I'm sorry, I shouldn't say things like that. I know. I guess I've laid out the beginning here, right? So I fill in the rest. So I initialize these lists, and here I've got. Okay, so I don't need to copy those lines again. All right, so Scott, I didn't answer what the zip function does. But Tanya did for me. So if I just have two different lists of things, if I do zip, let's say list, let me just do first of all list ABC. Right, that gives me ABC as that. If I do list 1, 2, 3, 1, 2, 4, let's say. Oh, what did I do wrong there? List ABC, comma. this takes, oh, sorry, I don't, yeah. I can just write this. Right, so those are two lists, and they're returned as a tuple the way that I've done this. So if I do zip of these things, what I will get is a Python iterable. But if I turn that into a list, and if I spell list correctly, then I get a list with A and 1 paired up, with B and 2 paired up, and with C and 4 paired up. So the reason I did that here is I have a list that is all of the weight matrices for each layer. I have a list that is all the bias vectors for another layer. And so now what I've got is I've got a list of tuples, each of which consists of the weight matrix for each layer and the bias vector for each layer. And then I'm extracting those as parameters W and B as I go through this loop. So what I'm doing is I'm assigning, first of all, the A, I'm calling the activations. I'm assigning A to be the input X just by itself. And then for the first layer, I multiply A by W and add B. Remember, this at symbol is just matrix multiplication. I call that Z, which is something that we'll call the weighted inputs, or I'm calling it the Z inputs when I accumulate these. So I accumulate the Z input, the weighted input Z. I apply my activation function to it and get an activation that I call A. And then I store these in my lists. So sorry, Alex, was you about to say something? No. Okay.
No, I'm sorry. I'll mute myself.
Okay. So if I do model equals initialize model dimensions, right? I'm just going to execute that again, right? And let me just make sure I've got dimensions set properly. (784,15,10). And remember, conceptually, I'm thinking of this, and let's just say I've got some X is equal to numpy.random.rand. And let's do this first. I'll say 784,1. Oops. And then what I'll do is I'll say print model.keys, right? So before calling forward, and then I'll do y comma model is equal to forward of x comma model. Now I'm using a functional style of doing this, and let me just show you what this does. And I'll do print x.shape, comma y.shape. Oops, what did I do wrong? Tuple cannot be interpreted as, this is an annoying NumPy syntax thing. There we go. Forward is not defined. I didn't execute this. There we go. Okay, so let me show you what happened. I initialized my model so that it had random matrices in weights and biases. Now what I've done is I've given it an input. So this input corresponds to one of these digits reshaped as a column vector. Okay? And what I've done now is I've taken that, I've passed it through my forward function, and it's given me as an output a 10 by 1 vector, which is in principle predictions on which one, probabilities of whether or not the resulting out, the input I gave is a digit 0 or 1 through 9, right? And notice after executing the function forward, I modified model and I output it again. And so now it not only has the parameters weights and biases and n layers, it also has a list that corresponds to the activations and the Z inputs. So what that means, I'm sorry, this gives us seasickness. Basically, corresponding to each one of these layers in my network, my hidden layer and my output layer, there is a bunch of matrices that are weights, a bunch of bias vectors. There's also a bunch of computed values, the Z inputs, or my weighted inputs that we call Z equals W times A from the previous layer. And there's also the activations, which is the activation function applied to that Z. And I'm storing those for the hidden layer, and I'm storing those for the output layer. And the reason why is I need those when I compute backward propagation. Okay, I'm doing this in a functional style where I'm modifying the function as I go along. I'm modifying my data. I could do this in an object-oriented fashion where I build the model and I associate all of these things. Instead of having these keys on this dictionary, I would have those as attributes associated, or attributes and or methods associated with an object in an object-oriented framework. But depending on your on how you'd like to think. Okay. So the reason why I stored these activations and these Z inputs is because once I've done a feed forward through my my neural network, my multi-layer perceptron, whatever. Again, there's ambiguity in what specifically those mean, but it's basically a neural network in which the things go forward, they don't go backward. There's no recurrence. And they can have different application functions. Then what I want to do is, in order to train the network, I need to minimize the loss with respect to the weight matrices and the biases. So what that involves is using steepest descent to do an optimization. In order to do steepest descent, I need to compute the gradients of the loss function with respect to the weight matrices and with respect to the bias vectors. So this involves a lot of hairy multivariable calculus. And this was discovered in the 60s or something like that, or the 80s, I think, is when the backpropagation algorithm was devised to do it. For those, I'm assuming at SciPy there's people who have multivariable calculus. If you're interested, Michael Nielsen's description from this book is beautiful. It's not that long. I've sort of carved it down here. This is the basic process of backpropagation. Number one, you take your input X, and then we'll assign that to some activation A0. Number two is the forward function, which is the one that we just wrote, that basically takes that input X, which we've reassigned, labeled as A0. And I've got a recurrence here that says take W for each layer, multiplied by A from the previous layer, the activation from the previous layer, add the bias, call that Z, and associate that with this layer. So Z1 would be associated with W1 multiplied by A0 plus B1. And that gives me Z1, which is my first weighted input. Then I apply my activation function to Z1, and I get A1, which is the activation of the neurons in my first layer. I then repeat for the second layer, right? I'll think of L equals 2 in my matrix, in my problem here. And I go through with the new weights, and I get compute a new weighted input for the output layer, a new activation for the output layer. I compute the loss. And then what we have to do is we start at the end of the output layer. I compute something that is called the error. And I apologize for this terminology. Error is a term that is overloaded. What it is really is it's really a derivative. It's a gradient of the loss with respect to the weighted inputs. And if I compute that, that'll be a vector associated with the output layer, the final layer. And here's a hairy expression involving a pointwise product of something I can compute, the gradient of the energy of the loss with respect to the output, with respect to y hat, if you like, multiplied by the derivative of the activation, the derivative of the activation function applied to the weighted input on the output layer. And those are multiplied element-wise. That's what this Hadamard product, this big circly dot thing means. And then I have another matrix formula here where I take where I basically compute the errors and I back propagate them through my network. So if I'm scrolling back up to my diagram. I should probably have just had this in another tab. So I compute the delta in this layer, and I use a simple procedure to compute that. I use matrix algebra to propagate that result back to this layer and to any preceding layers, but up until the input layer. I mean, something that involves the input layer. And there's some algebraic functions that express this. This is a derivation in multivariable calculus. I'm not going to explain what that is because it's hairy math. But it's not that. It's actually second or third year math for people who've done physics and math. But it's and it turns out that if you compute these things, these deltas, you can figure out, and if you have the activation stored from the forward feed step, you can compute the gradients of my loss with respect to every one of the the entries of the weight matrices and with respect to every entry of the bias vectors. That is the punchline. That is what all of this thing with back propagation is about. And the reason we want to do back propagation, does anyone remember what is the reason we want to do back propagation? Adjoint model for computing the diff backwards. Yes, that is another way to state that, if you like that. The reason we want to do back propagation is to compute the gradients because we need the gradients for steepest descent. And we use that to adjust the weights. Correct. Yes. Okay. So I went through, now if you take a look, there's I decided I'd give this for you. I figured if we tried to actually do this, I mean, we're doing all of this now. This is an implementation. I based it off of Michael's, of the version from Michael's book, but in fact, actually, I extended it because I had to do a little bit of tweaking. Yeah, I had to put in this extra detail here. Oh, I should point out, by the way, sorry, I forgot one thing. The way I've written forward, this works for batches as well. So in other words, if I had, instead of a single digit, suppose I had 3, right? Then I can push that through my forward propagation function. And the input is of shape 784 by 3. So each column of that matrix, there's 3 columns, are 3 images that have been reshaped into columns conceptually that I want to identify. And the outputs are 3 vectors of length 10, each of which gives the probability of which digit it is. So that works. In this case, the way I've set it up, the dimensions, the first dimension, the rows correspond, each row corresponds to a feature of my vectors, and each column corresponds to an individual observation in my batch. So 3 is my batch dimension in this instance. So I'm going to execute this. And I just want to check that I've done this correctly again. Remember, so let's just do print model.keys. Right, so this comes from after executing forward, right? And then for well, let me just do that first, right? And so notice it's got the activations and the inputs. So let's just say for WB AZ in zip model weights, biases, activations. And then finally, one last, I'll do the Z inputs. Okay, so I'm going to, again, this is just taking each one of those. These all have the same length. They should have length 2 in this case. And what I'm going to do is I'm going to print, actually, maybe I can steal what I did up here. This is what I want. Sorry, I know this is bad form. Okay, print. Okay, I'm not going to enumerate the layers, so forget that. Shape of W, W.shape, shape of B, B.shape. And I'm using an F string here just because I happen to like those. Shape of A.shape, and shape of Z. And we should be able to see what all of these things are, right? So for each layer, so my 2 layers in my hidden layer, the shape of W is 15 by 784. The shape of B is 15 by 1. The shape of A is 15 by 3. And that's because I had an input that had a batch of size 3. And so that has, each column is the activation that corresponded to each of the inputs. And the shape of B is, so that's not supposed to be B, that's supposed to be Z. Here we go. So this is what it is before. So now what I'll do is I'll execute backward. And so again, I give it some vector Y, which is a putative output. And so if I do Y is equal to numpy.random.rand 10,3. Model is equal to model is equal to backward. And let me make this a little bigger. Oh, did I execute backward? Hang on a minute, make sure I did that. Oops. I'm in Windows. I've lost my thing here. Shift tab. There we go. Oh, by the way, this is a useful Jupyter thing I do all the time. When I can't remember the calling syntax of a function, if you start typing the function's name, you put in the parentheses, you put the mouse inside there, and you hit Shift Tab, and you'll get a tooltip that gives you the doc string. So that is useful if you can't remember what the calling syntax is of a function, right? So these are useful little programming tips I like to use when I'm using Jupyter notebooks. Right, and so you'll see it's gone through and it's added some more keys to my model, right? Gradient of weights and gradient of biases, and those will be stored, and those should be the same size of the biases and the weights, respectively, right? So if I do for WB, DWDB in zip model, and let me steal my thing here so that I can type this quickly. Grad weights. I love tab completion. I know that I'm losing, that people can't always do this if they're And this is now too big here. Let me make that a little bit smaller. Come on, I'm frozen here. What happened? All right, here we are. Okay, print model.keys. And again, I'll take this thing here. Sorry, there we are. And this will be DW. And this will be DB. Okay. Right, and so notice that DW and W have the same shape. And oh no, DB and B, what have I done wrong? Oh, bugger. That is not good. That is really bad. Those aren't the same shape. Well, that's why we have testing. Crap, what have I done? How did I screw this up? This was working yesterday. Okay, that is not good.
David? The things that you are typing, are they similar in the instructor notebook?
Good question.
Or are you coming up with a new implementation?
Good question. These little checks that I'm doing here are not in instructor notebooks.
Okay.
I can save these and provide this to people after the fact.
Okay. Yeah, there's been some requests to have the code.
Absolutely. Part of the thing that I'm also trying to model is just my thinking process about this, because I've actually discovered a minor bug here. Let me see whether or not this actually causes us a problem. Okay.
There's also some feedback that because there's so much output, it's a little tricky to keep track and for people to type along.
Okay.
As you're completing the cells.
Okay. I will try and go slower.
Okay. Thank you.
The main point I want to emphasize is
I think there are some hints from people someone says Z-shape should be db.shape. I'm not sure where that is exactly.
Oh, yes. That's what I've done. Thank you. No, not that one. That one's the correct one. It should be db.shape. Oh, thank goodness. Yes, this is working correctly. Okay. Thank you very much. All right. So what we can do now, and I promise I will share this with you guys afterwards, is a quick walkthrough. So what we want to do is we want to take all that information and now do the update step, which is just to take the weight matrix, subtract the learning rate, which is called eta, multiplied by the gradient with respect to the weight matrix. And similarly, the bias vector gets updated by, and this is, you can forget about the math. It's actually a really simple thing to do. I think actually you guys can figure this one out. But again, in the interest of maybe getting things down. No, why don't we do it? Let's see. No, I'm going to cut and paste it in because we're going to get through this. Right. So, right. So I want to point out a couple of things I've done in the design here. So all I really did is that's it. This is really all that you had to add in there, right? And then we did this as a list, as a loop. We built up all of them, the updated weights, and then I reassigned those to the weights and the biases. And then I also decided to clear up my memory, so I deleted these other keys, right? So if I do this now, all right. After executing backwards, and if I type, oh yes, right, I go model equal, well, let's first of all print model.keys and do model equals update. Did I call it update? Yeah, I did call it update. And if I look at this, right, and I should have new, oops. Oh, I didn't execute this. Update required. Oh, update model. Oh, eta. I forgot to put in eta. Right. Let me put in 0.5. There we go. Oh, come on. Positional. Oh, yeah. That's what I get for being silly. Okay, there we go. Okay, so before I executed backwards, my model had a lot more information stored in it. And then afterwards, it had less. The reason I'm showing you this is because when you use PyTorch, and when you try and use the backward differentiation, the autograd in PyTorch to compute backpropagation, this kind of stuff is handled for you. It's done under the hood, so you don't have to think about it. However, if I try and do, things will screw up, right? So what will happen is if I try executing backward again now, I'll get an error because I need to do forward first, right? Right, so if I do model is equal to backward of y comma model, and what I get is I get a key error, and that's because it's looking to find these activations and Z inputs that should have been computed by forward propagation that haven't been done. Right, so it's I have to keep track of this extra things in the backpropagation algorithm, and this is done in frameworks. So how to organize this stuff is done in an object-oriented way in frameworks like TensorFlow and in frameworks like PyTorch, and there are design decisions on how that is done. But it doesn't. It doesn't matter anyway. So these have been updated by computing gradients with respect to whatever I had there. So now I know how to do that update step. What I can do is I can implement gradient descent, right? Actually, I think I can. Why don't I just do this straight up, right? So let's say,
David.
Yep.
So there's about 30 minutes left. There are some questions. Yes. There's about 30 minutes left to the tutorial. I just wanted to know to help you keep you on track, to be sure you make it to notebook 3 and cover the PyTorch.
Oh no, I'm just about at the end of this one.
Okay.
Great, thank you.
Mm-hmm.
All right, no, I so let me just do this quickly. So this is NumPy dot. I just want to make some random inputs and just make sure this works. And how do I want to do this? I want to have dimensions 0 right? Because that's got to be 784, and I'll have n batch here. I'm going to do this again. For y, I'm just going to generate some What I really just want to do is figure out what this is going to be. This is going to be dimensions -1, the last entry. And so now what I'll do is I just do simply model. Oh, sorry, let's say actually this is y hat. Right, so that's computed by forward propagation. I'll just do my loss as a function of y hat and y, I think is the arguments that I had. And now what I do is I compute the derivatives by back propagation. Well, that's just doing model is equal to backward of model. I think that's right. Oh, y model, thank you. And then I do model is equal to update eta, comma, model, right? And I can use that just to make sure I've done this correctly. Okay. So now I've got, and I'm going to iterate for 30 epochs. But I've got a little code here, and if I've done it correctly, then these should be going, the loss function should be going down, and it is. Right? You'll notice each epoch it seems to be going down, which is great. Okay. So I'm not gonna. I will quickly just cut and paste this in to make the plots, just because it's not that difficult, but I just want to make sure that we get this done. Okay, so all that I'm going to do now is I'm just going to do more iterations. It's the same thing. I'm skipping every it's 30,000 iterations, but every 500 iterations, I'll record it. Oh. Maybe I don't want to generate this plot. I can reduce the number of epochs, and I can reduce the size of the batch as well. Oh, come on, Google Cloud. All right, never mind. I'm gonna go to the next notebook, but we'll see what this is doing. But what this is basically doing, it just should be. That is really taking a long time. Okay, let me just go through the instructor notebook for the next one, because I know we do want to talk about PyTorch. And let's just see if this did finish. It's still not going. That should not be that bad. I don't know what's going on there. Okay. So what I want to do now in the last 20 minutes is do a whirlwind tour of PyTorch. I apologize. I know I would like to take a break, but I know you guys want to see some of this. And I want to tell you what the big ideas are so that you can get this down. Okay. So big ideas. We're going to learn about PyTorch tensors for working with PyTorch neural networks in PyTorch. We're going to learn about the autograd capabilities, which does the back propagation, so we don't have to do some of that pain. We're going to learn how to use a context manager, and we're going to see how Justin Johnson's example worked. So PyTorch, I'll just load it up. Did this other one finish? It is still going. That is crazy. That should not be that bad. Okay. So the basic principle in PyTorch is we use PyTorch tensors, which are basically the same as NumPy multi-dimensional arrays. So for instance, here is a NumPy array that is of type integer 64. It's all zeros, right? Here is a similar one that I constructed in PyTorch. That is of zeros. It's a 2x4 tensor constructed by torch.zeros instead of numpy.zeros. It's slightly different call and syntax. There's irritating inconsistencies in NumPy's API. So it takes a tuple 2, 4 instead of just 2 and 4 in sequence as a variadic argument. So when I run that, here is the output is a PyTorch tensor. The data type is a torch.int64 instead of NumPy int64. Right, so you can query all of these different things. It has a size method instead of a shape attribute. Which is a subclass of tuple, I think. So you can pull out its shape in NumPy. It's done with x.shape, and NumPy.shape. And the size is basically tells how many elements, which is the product of all the elements in the shape tuple, right? And you can see that is actually its own class. Remember, NumPy arrays and PyTorch tensors, they're homogeneous in data type, right? So, and that's because they can be laid out in memory and they can be worked on efficiently. And there's a lot of different things, right? Like just like you have NumPy.empty, you've got torch.empty, right? NumPy.once is torch.once, NumPy.random.random, there's torch.random for normally distributed random numbers. Remember, empty, that just allocates a memory, an array or a tensor in memory, which means whatever garbage is in that memory will just be interpreted in as whatever. So whatever is random bits. So the random bits in some chunk, 3x4 chunk of memory, have been converted to torch.short, which is a 16-bit integer. So these are random 16-bit integers that correspond to random bit patterns in the memory. Okay. You can also convert data like lists into PyTorch tensors, and there's using the torch.tensor constructor. With the lowercase tensor, it does some kind of inference from the data that you've got, what type of data type it is. With the uppercase T tensor, that's implicitly a 32-bit floating point number. Okay. And you can convert these things back and forth, right? You can convert a PyTorch tensor to a NumPy array, and you can do just as we can cast it from a NumPy array. So this is all that if you take a look at this link here, you can find some, it's a lot like learning NumPy. It's just exhaustive. But the thing that you should ask yourself is why the heck bother, right? Why go and re-implement all of the stuff that NumPy does for you if you have all that NumPy goodness? The reason why, there's two reasons why. Number one is you want to have automatic differentiation. You want to have back propagation so you don't have to write it quite so painfully. And that is what AutoGrad does in PyTorch. And that requires a data structure like the PyTorch array. And what that PyTorch tensor, what that PyTorch tensor does, in essence, is what we were doing with all of these functions here, where we were constructing these dictionaries. Sorry, let me, that were storing, building up all of these intermediate things in the computations. What the PyTorch tensor does is it provides internal data structures for managing that memory. Okay, so that's one reason to use PyTorch tensors. The other reason to use PyTorch tensors is GPU computation. So NumPy floating point values and integers and strings and various things, they're really good for work on a CPU on an individual machine. If you want to work on a GPU, if you have access to one, you have to use PyCUDA or some other framework or do low-level C and Fortran programming, which is really painful to do. So PyTorch provides an interface where you can take the advantages of GPU technology, which is a big reason that deep learning has come a long way, right? So the advantages in GPU technology for pipelining matrix vector operations element-wise efficiently has had a huge impact on why neural networks are actually feasible today, whereas they weren't, say, 10 or 15, more so than they were 10 or 15 years ago, we'll say. Right? There's also improvements in algorithms and technology. Right, so I just created this object A, which was a NumPy array, a PyTorch tensor, right? So I just want to say, it has an attribute called a.device, which is CPU, because that's what I'm using. If I were using a GPU, I could specify when I create tensors whether or not it's going to go onto, say, a device of type CUDA if I have a GPU available to me. I'm not going to talk about that today. You can take a look at how to do that in the PyTorch tutorials, but I want to focus on the automatic differentiation because that is kind of a good takeaway for us to end after all of our painful discussion of backward propagation. So if you take a little calculus problem, right, like just differentiating this polynomial, right, and then finding out its derivative. You can do that in Mathematica and Maple and computer algebra systems. But if you have a data structure like a PyTorch tensor, you can define it with an attribute called requires_grad. And setting that to true means, hey, I'm going to do some computation like I do with that forward function we wrote in the last notebook. And when I do that computation, I'm going to store things that happens to that computation internally inside my tensor so that when I have to do back propagation, I can figure out what the gradients are. So for instance, here I've created this X object. Actually, let me do this first. Let me take false, right? And when I type y.grad function, I evaluate this polynomial explicitly on the tensor X, and I print y, and nothing is there. If I change this and re-execute again, and I change this to true, the default is false, right? Now what happens is my tensor replied, right? F of x, if x is 2, is 51, which we can just learn from high school algebra. The value is 51, but I also have this thing called a grad function, which basically comes down to the fact that PyTorch AutoGrad knows first-year calculus. It knows how to differentiate a polynomial. It knows how to differentiate a whole bunch of functions that we know how to work with, right? And that grad function is this abstract object that will be used. Basically, it'll be the activation functions when I'm doing the gradients of the activation functions when I'm doing my back propagation through the network. So it turns out that instead of writing a function for doing backward propagation, my PyTorch tensor, as long as it has been created with requires_grad equals true to the inputs, it has a method called backward. And when it does, it back propagates derivatives to the things it depends on. So y was created using the tensor x. So if I use y.backward, then the x has an attribute created, which gives us the value of f prime. So this is the derivative of f of y with respect to x, which should be 87, which is in fact what it is here. So invoking y.backward it causes backward propagation to happen. And if I try and execute y.backward again, I get a runtime error. And that's because the memory has been freed that I used. Right? Remember on this notebook, when I computed the backward function that I wrote, if I did it once, and if I did the update, I cleared off my dictionary, erased all my interim data structures, right? So if I try and call backward again, I've erased all of that data. That's exactly what this error is in PyTorch. Sorry, I'm switching back to the notebook 3 here now. I know I shouldn't do that. I apologize. Okay. So here's another back propagation example, just with a composition of functions, right? And if I go through this and I look at this, I can see that I get computed a tensor, which actually gives us the same thing if I did for the function that I had up there. Z equals cosine of u, where u is x squared, and x is square root 3 of pi over 3. So I should get 1/2 when I evaluated x equals root pi over 3. And I think I do. And I also use this item method for singleton tensor. This is a singleton tensor. If I want that as a scalar, I have to extract that as x.item. Okay. So let me just point out some of the things we can do here. And I've run out of time. I've got 10 minutes left. I think I'm not going to try and go through this, but I think you can go through what I have written here, and you can also go through Justin Johnson's example here. And I think what I have written now should be more intelligible than Justin Johnson's example before you took. I think if you had tried to read this before you took this tutorial with Hugo and I, it would have been more confusing because you would have been reading these things and wondering what the heck is all of this. Now I think you're armed with enough knowledge just to be a little bit dangerous. So rather than trying to race through and execute this is my first NumPy version of this. My notation is a little backwards relative to Justin's because I used w times x plus b instead of x times w plus b, which was consistent with the math book where I got the derivation of backward propagation in order to get it to work. So I apologize for that, but it is a good skill to have. And then here's just the update steps and and the back propagation done explicitly. When we convert it to PyTorch, all of this is done in a few steps, and I get a much shorter piece of code. I could actually do this a little bit more neatly. But I think in the interest of making sure that I don't leave anyone in the lurch, let's look at some questions now. I'm going to stop sharing my screen. I will make sure to share my notebook with my my little on-the-fly thinking so that you guys have that available to you. Yeah, I know. We'd love to do that, and only for that MNIST example. I didn't get to it. I wanted to try and debug it, and it just added another. On my next iteration of this tutorial, I will do that. But thank you, Martha. Sorry, let me take a look at the questions. Which 5 questions are the top? I have
some for you. So there's the eternal question. Hopefully not eternal, but people are asking, can you talk a little bit about the difference between TensorFlow and PyTorch? People are particularly interested in why should I move from one to the other? I know it's a tricky, somewhat political question, but if you could give some context, that would be great.
No, I have. So, first off, full disclosure, I'm biased because I work closely with the PyTorch development team at Quansight. So I have more familiarity with it. I think it has the advantage of being new on the block. So it has certain design features that are more elegant and nicer, I think, than TensorFlow has. And the other thing is I would use Keras first before using TensorFlow. TensorFlow has all the low-level bits. Keras is a high-level user interface API so that you can actually work with TensorFlow more neatly. PyTorch has something called torch.nn, which is a related thing. But the thing you've got to ask, if you're doing this for your own learning and your own projects, that's one thing. If you're doing this in a if you're working in a production environment where people are using TensorFlow versus PyTorch, the question has been answered for you, right? You don't want to take on the technical. Maybe there's some technical debt, but I think that it is it's a tough question. Okay, let me see what else. Why was defined? Okay. No comment on the learning rate. Okay, yeah, that is a good question. Learning rate. So learning rate is something that you can. So this is you can change. You can have that change adaptively in your optimization algorithm. I would say, yeah, it is like all things. So there's not only did I have no comment on the learning rate. I had no comment on choosing the architecture, right? I don't know why macOS does not support GPUs with PyTorch. That's probably something to do with the availability of the GPUs on macOS, but that seems strange to me because I know that Macs often have GPUs. I didn't comment on on how you choose the network architecture, and again, this is the classical black box questions that people ask about machine learning? How do I choose the hyperparameters for k nearest neighbors, right? How do I choose the depth for my decision tree? How do I choose the number of neurons in my internal layers, right? There is no, it's very unsatisfying, right? There are and the answer is it's always going to be domain dependent. The data that you have will have some structure to it that will reveal what that is. And data scientists spend a lot of time playing trial and error. Exactly, Ahmed. Thank you. So what you want to do is you want to be able to use a nice framework like PyTorch or like Scikit-Learn, in which you can experiment. You can write a short bit of code like I just wrote in this notebook. You can experiment with that code and iterate quickly in notebooks when you change in a new data set and when you sub in new parameters. And then you can iterate those, and then you can write that programmatically and then get that fed, run on your cluster overnight. Learning rates. Well, usually learning rates, you kind of do it adaptively. So you start with large learning rates just at the beginning of the training because you need to take long steps in order to get to the right part of the space. And then as you get closer, and the loss is sort of leveling out, you start taking smaller steps so that it starts until you get someplace. And again, you don't want to take too many steps because you'll end up overfitting. It's it's the same terminology that we use all the time in machine learning. It's just we're applying it in this case to particular to neural networks, and deep learning being a particular thing for supervised learning classification type problems. We could apply these things to other classes of problems as well, but it's for unsupervised learning, but we didn't quite get to that. But I'm hoping, I don't think I've got much. I've got maybe time for one more question. I think we could.
Okay.
So I thank you all for coming. This was delight. This is weird. I would much rather have been in a room with people, like wandering around, seeing people's faces. But this is the world we live in right now. So, but nevertheless, I appreciate you all bearing with us, with Hugo and I, with poor Hugo's injury. And I appreciate really, there's a form that Hugo had linked somewhere in there. Can someone find where that was and repost it?
Yes.
If not, we'll put it in the Slack channel. If you guys have other questions you want to ask, put it into the Slack channel and I'll make sure to follow up. I'll make sure to follow up when we repost the stuff. I'll push stuff up. And I will make sure that the stuff that I scribbled in my instructor notebooks gets feedback to you. Okay, so don't worry about that stuff. I hope you learned stuff. I hope you had fun. I hope you got a stronger conceptual foundation so that you can actually take a look at the tutorials on the PyTorch website now, and they actually make sense. I think that's kind of what my goal was. I think that if you're at that stage, you can go out and you can cause a little trouble.
All right, I'm going to paste in the link to the Slack channel right now in the chat, and I'll paste again. I lost the link. Hugo's feedback form.
I'm loving all the love I see in the chat, guys. That's it. It makes me feel good. So thank you.
All right, thank you, Dhavide.
Put that in the people
Thank you, Hugo.
We'll figure out what we can fix.
Yep. Thanks, everyone. I hope you have a good rest of your day or a good night, and we'll see you tomorrow for another round of tutorials. And for those who are staying awake, enjoy the sessions this afternoon. Goodbye.
Thanks, Alex. Thanks for all. And thank you, and Tanya and everyone else.
Yeah, thanks, Tanya, for answering so many questions, being the silent force behind this tutorial. Bye, everyone.